think that there is, yeah, sort of figure out what that is. Yeah, this is AI.
It's close enough. Yeah. No, like that. Yeah. There's only one screen. Yeah. This is so fun.
All right, great to have everybody here. Super excited to be running this workshop on theoretical foundations of human AI complementarity. This workshop is an IDEAL workshop. IDEAL is the Institute for Data Econometrics, Algorithms, and Learning. We're gonna have a brief overview of some of the things that IDEAL is doing, and then I'll turn it over to Jessica, who's gonna introduce the workshop. So IDEAL is a Chicago area institute on foundations of data science that has participants from 5 major universities in the Chicago area, as well as Google as an industrial partner. There are a large group of faculty, 60 plus, at the different universities in the Chicago area who are involved in IDEAL. And it spans a number of fields that are all exploring fundamental contributions to data science. There are 3 main research thrusts that IDEAL is interested in: foundations of machine learning, high-dimensional data analysis and inference, and connections between data science and society. This workshop is part of a special program that we're running at IDEAL this entire fall. This is actually the first workshop of the program. September 26th is today. And there are a number of other workshops that please pay attention to, because we'll be putting them on, and a number of ways to get involved. There are some co-listed courses. And at Northwestern, we're running a PhD seminar on calibration. Cool. So with that, I'll turn it over to Jessica to introduce today's agenda.
Hello, everyone. So yeah, we wanted to talk about this topic of complementarity, which is often what we hope to achieve when we have a human and a statistical model and we want to put them together. Complementary performance just means that the pair is gonna, perform better than either agent alone would on some decision or prediction task. This is very hard to design for. People have been trying and sort of making this assumption we should just see this when we put any, human and predictive model together, and that's of course not necessarily true. So we know from research going back to like the 70s that when we're comparing a statistical model and a human on some, tasks, some prediction tasks, that the model will generally outperform the human if we're testing on, data where the model, which sort of comes from the same distribution the model was trained on. So this makes sense. Like a human can't necessarily do better in that context. However, in reality, we often think humans might have access to different information or be able to interact. Say, you have a doctor who's making some diagnosis decision assisted by some prediction model. We often think, this human might be able to get more information from the patient, et cetera. And so there's a lot of interest in sort of how do we design kind of the best workflows when we have a human and a model. And so it becomes important to understand, the information the human has, what sort of strategies they're using to combine information from themselves and the model, what kind of weaknesses they might have in terms of anchoring or other kind of heuristics they apply. And so, once we have a better understanding, we can then, try to optimize, find a workflow that works best. And so today we have talks from 4 exciting speakers who are all working in this area, slightly different angles. So we'll hear a bit on the behavioral side, but also a lot on the sort of theoretical side. How do we think about the optimal pairing? So we will get started right now with Hussein Mazner. So Hussein recently got his PhD from MIT, working with David Sontag earlier this year. In fact, he's now a senior researcher at Microsoft Research in the AI Frontiers group. So his research focuses on augmenting humans with AI to help them complete tasks more efficiently. So he's done a lot of interesting work in this space, looking at things like models to optimally sort of learn to defer to a human in some settings, onboarding a human who's going to use an AI, they need to know enough about the model itself to use it well, and done work in particular that has high impact on things like Copilot and in the health sector. So his talk today is who should predict conditional delegation in human AI teams.
All right, thank you so much, Jessica, and good morning, everyone. Just need a minute to set up here.
Sure, yes.
All right, perfect. All right, so today I'm going to talk a bit about this concept of conditional delegation.
Sorry.
Let me get rid of that. Yeah.
Thanks.
Of conditional delegation in human AI systems. So I'm going to break it down to start with and think about what is this human AI team. So we're given as input a very well specified task, and we have this human component and AI component, and the human AI communicate with some sort of channel to send messages back and forth, and then continue doing so until they produce a final output. Now, what makes this a team is communication between the human and the AI. And one key aspect of communication is delegation of work between members of the team. And I think delegation is really the most important aspect to make this human AI team perform well. And this is going to be the main focus on the talk today. So to think about delegation as part of this communication channel, I'm going to try to separate the two types of messages the human and the AI can send to each other. So I'm going to say one type of message is the delegation messages. And then there's other messages that they can communicate between each other. Now, to make this concrete, I'm going to take a few examples. And then before I do so, I want to really restrict today's talk to unilateral delegation. So I'm going to think about either the human is in control of the whole process and can delegate tasks to the AI, but the AI cannot delegate back, or the AI is in control and can delegate tasks to the human, and they can either delegate the entire task or subtasks and the bigger task that they're trying to solve. So now let me make things more concrete. So one example is the human in control, and they're delegating the task to the AI. So the task is to classify a certain tweet as toxic. So take your belated and fulfilling prevarications elsewhere. And so the process starts with the AI first sending a message to the human with their prediction. So the AI says, no, it's not toxic with this probability. And the human is not an English speaker, and they don't know any of what these words mean. So what they will say is, AI solved this task. So they'll send this delegation message, and now the AI takes control and sends the final prediction of not toxic. Now, another example is in reverse, where the AI is in control, and now they're delegating subtasks. And so now the task is this tweet toxic? So this is in Arabic. And here, the AI is going to first start by saying, oh, translate this tweet for me, human. I don't speak English. Oh, sorry. Was there a question in the back? Or
The question was more about whether, for example, in the unilateral model, can the human ask AI, I would like to delegate to you one of the following three tasks, which one do you think you're better at? So is that interaction pre-delegation allowed or not really?
Not really for today. So it's really more like either delegate the entire task or I'm going to give you a specific defined subtask to delegate. So I will say, oh, I'm going to delegate the subtask, which is translation. I'm going to get back from the human this translation, and then I'm going to integrate that to make my final decision. So this is another example of this mode where now we've reversed things. And the outline of today's talk, first we're going to start to think about the setting where AI is in control and AI is either delegating the entire task, and we're going to call this problem learning to defer, or the AI is delegating subtasks. And this setting is really important because it allows us to automate a fraction of the tasks while having the safety of this fallback option of letting the human predict if the AI recognizes it's going to make an error. So we're not quite there to full automation because of AI errors. So this setup is going to allow us to have that safety. And the other setting is the reverse one, where the human is in control and it's going to delegate tasks to the AI. And we're going to dub that setting teaching to defer. We're also going to look at the setting where we're delegating subtasks. And this setting is important because we're reducing the effort the human has to make, because maybe the AI can solve part of the problem. And it allows to have this human oversight of verifying AI's decisions before they get rolled out. So let's get started on the first part of today's talk. And this talk is based on the following papers, just for your future reference. So let me introduce this problem called learn to defer. So we start with a task, which we're going to denote by X as from the perspective of the AI model, and Z from the perspective of the human. And I'm differentiating the task based on who can observe information about it. So the human might have some side information about the task that's not revealed to the AI. And so they have asymmetry in the information sets that they're allowed access to. And we start off by the AI having control, and the AI makes the delegation decision using its delegator function R of X. And so if R of X is 0, the AI is going to make a prediction with its classifier M of X. Now, if R of X is 1, the AI is going to delegate or defer the decision to the human, who's going to make their prediction with their predictor H of Z. Now, this is the setup. So we have the AI first taking control, delegating to either itself or the AI or the human, and getting a final prediction out. So now let's write out the optimization objective in this setting. So I'm going to assume I have data of the following form. I have tuples X, H, and Y, where X is the context from the perspective of the AI, H is the human prediction on this example I, and Y is the ground truth label. And of most importance, the prediction of the human is not necessarily the same as the ground truth label. So we're implicitly assuming that the human may not be perfect. And our task is to optimize the AI classifier and delegator jointly. So given a ground truth Y, our loss function is going to be to compare the final prediction of the system to Y. So we can look at this equation, this loss of deferral, which is a function of M and R, the delegator and the classifier. And so if R is equal to 0, the final prediction is going to be M of X, and we're going to compare that to Y. And if R is going to be 1, we're going to compare the prediction of the human H of Z to Y. So it's a very simple misclassification loss that we're considering. Now, what is the optimal solution to this problem? So without any data or computational constraints, we can write down explicitly what the base optimal solution is. And simply for the classifier, it's going to look at the conditional probability of Y given X, and what is the class Y in the labeled set calligraphic Y, it has the highest conditional probability. So this is the same as a multi-class classification problem. Now for my delegator, it's going to compare the confidence of my classifier to the confidence of the human model. And so it's going to compare probability that M is actually correct given X to the probability that H is correct given X. And this is where this asymmetry in information sets is really important. If the human had access to the same information set X, as does the AI, then you would never delegate to the human, because the optimal solution is to always have the AI predict. But because the AI might have some advantages, then the optimal solution would still allow for some potential delegation to the human. Now, this optimal solution really inspires a two-stage process to solve this problem practically. First, you learn your classifier as you did before in a standard machine learning process. And now to delegate, you try to estimate the confidence of your classifier to the confidence of the human model. Maybe you build a proxy of the human, and then you just compare those confidences post hoc. So that's a very simple baseline that you could do practically to solve this problem.
Just to clarify,
There's a question.
when the task is delegated to human, does the
Yes.
human take into account, does the human make an inference from the fact that it's been delegated to her and account compound with her own signal?
That's a super interesting question. So the question is, once I delegate to the human has this knowledge of how I was delegated to. And so there's also the question of what information I should give the human once I delegate to them. There's been some preliminary research with user studies that show the best thing to do here is to tell the human you've been delegated to, but not to give them information about what the AI said, because there's a reason why the AI delegated. And so once you give a human more information, actually their performance decreases. But in this theoretical setting, I'm assuming the model of the human, whether it's been delegated or whether it's operating in the wild, is the same. So this is a simplifying assumption.
Even in this model, from the fact of being delegated, so your prediction is not your a priori prediction, but updated prediction.
Of the system, but the human model is like fixed here. Rather, it doesn't change with the fact that I'm delegating. So that's a assumption I'm making.
Okay, that's a bit.
Yeah. And so what I want to show is that this two-stage solution is not the optimal one to make. So I first started by saying I'm going to learn how to classify and delegate jointly. And so this is my joint procedure, and I'm going to try to compare that to this two-stage process of learning the classifier first and then delegate, figuring out when to delegate, versus this joint process of classifying and delegating. And this gap between these two methods is really going to become apparent once I have computational constraints on my classifier and my delegator. So I'm going to assume my classifier and delegator live in some hypothesis class. I'm going to denote it by R for delegator and the M for the classifiers. And then I'm going to compute the VC dimension of those classes. So that's D of M or D of R in this equation. And this delta is a minimax gap between the joint solution versus that two-stage solution. And to explain simply, the gap between these two procedures is inversely proportional to the size of your classifier, to the power of your classifier. So if I had a classifier that was infinitely powerful, this gap would reduce to 0. And it makes sense, because if I have infinite power, I don't need to focus on the subset of things that the human is not good at. I can just try to do my best overall. But if I have very limited resources, I want to allocate these resources to where the human performs badly at. And so I allocate my resources there and delegate to the human on the other side. And so this really proves that if you were to try to solve this optimization problem jointly over the classification and delegation, you get some benefit. Now, if you were to do this practically,
Could you just say it again, the differences between, so two-stage means what?
Two-stage means I build my model and classifier model independent of the human. And then to delegate, I post hoc, take this classifier I learned first and then compare its confidence to the human. Jointly is take this optimization problem I wrote down and then solve it with respect to M and R at the same time.
Jointly means I'm potentially changing my classification depending on whether or not I delegate?
Yes, exactly. So I'm learning this one model that delegates and classifies versus learning first a model that classifies and then a model that delegates.
Can you say a bit about in which cases that would make a difference? So intuitively, if I could have an oracle model conditional on X, I would still take the same decision whether it's delegated.
Exactly. So it only matters if you cannot have an oracle model, because you have constraints of how expressive your classifier is. So if your classifier cannot be fully expressive, then you benefit from complementing the human on the subset they perform badly at, and then delegating on that other subset. And this is just theoretical proof of that.
So
Yes.
here we assume the AI knows the perfect model for the human. Is that correct? When they do this optimization.
Yes, here I can just assume I have infinite data for this theorem, but practically we're going to look at the procedure that just learns from any data set of human samples. All right, so now we want to solve this optimization problem. So try to solve for M and R given this loss function. And we quickly run into the same issues you run into when you're doing classification, that it's really computationally hard to solve this problem jointly, even in the simplest setting, where you have linear classifiers, and even if you have zero error, that's possible. And what we do is in machine learning is take this objective function and find a surrogate function for it that's differentiable, that's possibly convex, and it's nice to optimize. So that's what we're going to do.
Okay, quick question. So here when you say that it's true even for linear models, this is for the hypothesis class doing.
Hypothesis class.
What about the delegation class?
It's also linear.
That's also linear.
Yeah.
So is this coming from hardness of agnostic learning or something?
So it's coming from hardness of learning half spaces.
With non-realizable setting.
In the realizable setting and in the non-realizable setting. This reduces down to learning a half space, essentially. Sorry, intersection of half spaces. Intersection of half spaces. Yeah, sorry. Intersection is the keyword. Okay, so to build this surrogate model that we can optimize, we're gonna take the log likelihood of the human AI system. So instead of looking at this hard, conditional probability, we're gonna take the log likelihood and then apply distance inequality. So now we get this expectation of the log, and it's really the same terms as before, but now everything is a probability. So now I have probability of my classifier saying something, probability of deferring, probability of the human, probability of not deferring, and so on. And so here I'm going to allow my classifier and my delegator rejector to be probabilistic, and I'm going to parameterize them in the following way. I will define a set of scoring functions, G1 to GC, for each label in my label class, calligraphic Y. And I'm going to define this extra scoring function, Gbot, so G with this inverted T. And these are going to come from the same neural network in practice. And I'm really, the only thing I'm modifying from a standard model is I'm going to add this extra output head. And now the way I'm going to define my classifier and delegator is as follows. The classifier is really as usual. I'm going to take these scoring functions and I'm going to apply softmax to them. So this exponential over the sum of exponentials. And that's going to give me the probability of my classifier predicting a certain class. Now for the delegation decision, the probability that R is equal to 1, I'm going to take this extra output that I created, and I'm going to check the probability of that compared to all the other logits. So essentially, I only delegate to the human if this new output has a higher value than the maximum of all the others. So I kind of turn it into C+1 classification tasks. So if I had, if I was predicting 0 or 1, now I'm predicting 0 or 1 or deferring. And I only defer if the highest logit is the one for deferral. And I just plug in this parameterization into my log likelihood, and I get my realizable surrogate. And it really looks very similar to the cross entropy laws, but in this numerator now, I have this extra component, exponential of Gbot, and it only exists when the human is correct. So once this indicator that H is equal to Y, so when the human is correct on this example, you as a learner have the choice to either predict the label Y or to predict to the defer, because both of these options give you the same cost. And so it's up to the flexibility of the model to learn which is simpler for it to make. And kind of for theoretical validation of the surrogate, we find that if there exists a human AI team that has 0 in the original objective, this realizable surrogate will find that optimal solution. Now, if there does not exist a human AI team with non-zero error, so if I have epsilon error, I have no guarantees that I can make. So it's really a restricted setting, but it applies to the setting where I have bounded computational resources. And just to sum up, basically, this learning to defer setup, instead of your traditional machine learning model with these C output units and train with cross entropy, I'm going to add one extra output head. I'm going to swap out cross entropy with this surrogate. And now I have a model that knows how to defer to the human. So I have a couple of simple empirical validations to show. There's much more in our paper. But essentially, this is, again, going back to the theory of this gap between a joint procedure using the surrogate versus that two-stage procedure. And so here on the x-axis, I'm plotting the kind of complexity of my classifier class. So essentially the number of neurons in my neural network. And the y-axis is the gap in accuracy. So you can see kind of when I have these limited resources, I really benefit from using the surrogate. But as my classifier really grows, this two-stage, this kind of fancy two-stage joint procedure with the surrogate, really, its benefit becomes limited. And you can make the same argument instead of model complexity to sample complexity. So here on the second graph, I'm plotting on the x-axis the training data set size, and the y-axis is my system accuracy. And I have this black line for joint and blue line for stage. And you can see kind of the gap narrowing as I have more data. But in the low data regime, I really benefit from smartly allocating my classifier resources.
So in the plot on the left,
yes,
one is staged. Stage is all at one.
No, so here, I'm plotting the difference. So it's a gap. So they're showing different things. Here it's a gap, here it's absolute.
Stage.
Yes.
Got it, not the.
Sorry.
Black line.
Yes. Yes.
On the graph on the right, what's the classifier complexity?
So both are fixed. So it's a convolutional neural network of like fixed dimension for
like number of parameters, if you have to guess.
This was 3-4 years ago. So this was probably like ResNet 16 or something like that, if I remember. Yes.
For the evaluations in the case of when it did delegate to the humans, did you have a human classify everything ahead of time and then you just decided the delegations? How did you do that?
I have a data set, like my test data set has a human prediction for each example. So I keep those human predictions for only the ones where I delegate. So that's how I compute my test error.
So the delegation decision is for that question had nothing to do with the human.
Exactly. So the human is kind of an a priori model. But that's really the only thing you can possibly do in a machine learning setting. Because otherwise I need to have a model of the human. So it becomes really hard for me to learn a priori.
Today.
Today, yeah.
Another question. So do you have a sense of what kind of samples qualitatively it's good to defer on? For example, in active learning, you see that typically near the decision boundary, you would like to get, labels. You ask, queries and get the label of links, near the decision boundary. Is it something similar here, or
it is something very similar. So the simplest baseline is just to defer when your model is not confident, and that's a strong baseline. But then you find some quirks in your data where the human classifier just makes error. In the second part of the talk, there is a bit more description of where to defer, and we actually have procedure to kind of qualitatively describe those regions. In fact, there are more questions. Yes.
Did you look at all like whether there are kind of weird regions, as you say, where you can kind of systematically do the opposite of what the human says, because that's an area where humans are prone to choose exactly the wrong thing?
So that would work in a binary setting, I guess. So this is a 10-way classification task. I haven't tried that exact thing, but I don't think will be that simple in reality, probably. Yes.
As a follow-on, have you ever thought about the relationship of this to what used to be called meta learning, but I think meta learning now has a different term. We have multiple classifiers, and you're deciding between them that the delegation system seems similar to that.
Yeah. So this is very similar to the mixture of experts literature. But there's a really crucial component is in mixture of experts, you're learning the router and you're learning each of the components. Here, one of the components is fixed. So if you apply the standard methods from mixture of experts, you find that they fail in this setting because they're not used to the fact of, first of all, not having probabilities from that model. So the human, I only have this discrete samples, and I don't have the probabilities. I really need those probabilities for those mixture of experts loss to work. So that's why we had to derive all these circuits to begin with. All right, I'm gonna skip this. Sorry.
Do you have ground truth the same as a human label? Like, what's a ground truth?
So the ground truth here is different. So for a more realistic setting, on just X-rays, so here the ground truth is so this is a setting where you have a chest X-ray and you're trying to predict like one of many diseases, and the ground truth is the consensus of 5 radiologists, and then the human prediction is a single radiologist. And so that's what you're comparing, label Y consensus versus single human. And so this is another evaluation where we can see kind of where my radiologist is, where my AI is, and these 3 are kind of different procedures to do this delegation smartly, and you can kind of outperform the radiologist on their own with only using them 50% time, even though this model is actually worse than radiologist on this task. All right, so I'm going to move on to the kind of the second part, which is delegating subtasks. And here really it's really the same setting as before, but now I have this concept of time, and at each time step t, the model can decide to either delegate the subtask with a delegator r sub t at time t, get a message back from the human, and then this, you just imagine this in a loop essentially. And I just want to give an example of a almost hypothetical AI model. And so really the task here is, can you register for the human in workshop at IDEO? So this is really a complex task. And so the AI would start with, first decides not to delegate. So it searches for ideal workshop on Bing, not Google. And so it goes to Bing, says ideal workshop, finds the link, great. Then it decides, oh, I can still solve it on my own. So it decides not to delegate. So R at time 2 is 0. So I'm going to click on the ideal workshop on clustering. The third step is it's gonna go to this ideal site and it's gonna click on events. And the events stop at fault 22 and there's nothing about human AI. And so now it's stuck. And so it says, delegation at time 4, I can't seem to find the human AI workshop. Can you help? And so now the human can just type in, oh, this is the right link. You weren't on the wrong old link of IDEO. And so now the AI can take this new link and then now click on the wrong workshop again. But essentially, this is something that's going to be, real sometime very soon. And we really need to figure out how to delegate subtasks. So this is really work that I'm trying to do now. And I just wanted to open it up. And so really, how do we train AI to delegate like subtasks? And the approaches from the first part for delegating tasks really don't work because the setting is very simple. Do you know exactly what will happen? Almost exactly if you had delegated or if not. But here you have infinite choices for delegating and you don't know a priori what the human would say if you made a different decision. So we really need new methods, maybe inspired from offline RL, to learn from past policies of AI solving with the human in the loop, or ways to learn online on the fly with the human, using some type of methods. And the other side of things is once you bring in the human into the loop, you have to catch them back up on the context pretty quickly. And if you're solving a complex task, you don't want the effort for the human to solve this specific substep to be, more than if they just solve it on their own. So we need better ways to catch up humans and really help them help us solve these subtasks. And there's really many exciting subproblems in this area. All right, so I'm going to move on to the second part of my talk, where we speak about humans in control now. And now they're delegating entire tasks. And so the setup here is really what's called AI decision making, where the AI first sends a message to the human with their prediction. So we're going to call that A. And the human now has their own delegator, which is a function of the input task X and the message of the AI A. And now the difference is that this delegator is an internal function for the human, which we don't observe. We only observe its prediction. So that's what's also commonly referred to in the literature as the mental model of the human. So if R of X and A is 0, the human decides to solve the task using their own model, which is a function H, X, and A. Now, if R is equal to 1, then we delegate to the AI, and AI solves it with its own policy, Y subscript Y of X. So it's really very similar to the previous setup, but now we just inverted everything. And similarly, we can write down a very similar loss function. And so, I compare the ground truth to what this eventual system says, which is governed by the human delegator R, human predictor H, and the model classification by subscript Y. And here I can assume I don't just have access to the human prediction, but they're also their past delegation decisions that they've made. And looking at this equation, there's many things I could try to optimize. So as before, I could try to optimize the AI model pi, subscript Y, or the AI's message A. Another thing that's a bit funky is I could try to optimize the human. So I'll try to optimize how the human makes decisions. And we'll show examples of both of these two options in this talk. So this teaching to defer objective function I write is the same kind of objective function as the one from the previous talk, very slight differences. And really the reason I can't just apply the methods from part 1 to this setting is that in part 1, I assumed the model, the AI is differentiable. I can take gradients, I can do these loss functions. The human is not differentiable. So I can't just, apply my gradient descent on the human. And in fact, what optimization is going to mean here is it's going to mean teaching. So in the literal sense of sitting the human down and teaching them this delegation function that I can learn.
So why human is not differentiable?
I mean, I don't know how to do torch, import torch, human, equal network. I mean, that's the exact sense.
It's about not knowing the model, I guess.
I mean, even if I know the model, I can't upload the delegator to your brain.
Okay, you gotta optimize.
It's
not
optimizable. Okay. I'm being silly, but yeah. So really to teach the human, now I have to kind of make a bunch of assumptions about how they might learn. And this really assumptions are not based on anything. They're just kind of a model I thought made sense. And so I can assume the human has a prior. So they make decisions in the past with some delegator. And then as they observe new data of interacting with the AI, they update their prior in a local region around the data points they observe. So that's how I have my posterior updates. So I have a prior and I have a mechanism to update that prior. And essentially I'm going to exploit that kind of very high level thing I just mentioned to try to come up with a way to teach the human. And so essentially teaching, I'm going to try to take the human prior and have it match an optimal delegator, which I can learn algorithmically using the tools from part 1, and as few numbers of data regions. So now I have a thing called teaching complexity. So I want to make sure I make the human catch up with as few number of data points. And one of the objectives, I think I'm running out of time a bit more than I expected. So one of the tasks we've evaluated on is this object detection task, where you're trying to predict a traffic light from a very blurry image. So here are the humans making predictions, so they can say yes, no. And the AI gives you their prediction. So a binary decision with a probability. And if you can squint your eyes, there's a bounding box there. And you can press this button and use AI answer, essentially delegating or solving it on your own. So that's how I get my data from. I'm going to try to very quickly go over this. So again, recall, this is my delegator, R of X and A. So red is ignoring the AI and blue is using the AI. My first step is learning this prior of the human. So in this region defined by X and A, they use the AI answer in all of this blue region and ignore the AI in this tiny red region. Now, as I said, I'm going to compute an optimal delegator. So assume I have a data set represented by these points X. I can label each point with what the optimal decision the human should make. And so one refers to using the AI, and which is correctly classified as blue here. But 0 refers to ignoring the AI, which should have been red. So essentially, if I looked at this region, I should find kind of these two clusters in my data that will turn the human's delegation function into the optimal one. So now I've classified every point correctly by hopefully informing the human about these two clusters. Now, how do I convey to the human that, look, there's these two clusters of data points where you're making incorrect decisions on? You should trust the AI. So how do I convey that information? And the simplest way to convey that information is to try to describe these regions. So essentially, I take each region, and I'm assuming each point in my data set I can describe in natural language. And I try to describe that region with a large language model. So I take points from inside the region, so in blue, and I take points from the boundary outside the region in white. And I ask the language model to contrast these 2 points. And so this is important because if you want to try to describe a region, you want to describe its boundary. So without these points outside the region, the model doesn't have a reference point to really delineate the region. And there's a kind of a bit more fancy algorithm in the paper to know how to select the points to inside and outside to get that description. So now at the end of this, I have a set of regions, each with their description. And the way I'm going to teach is for each region, I'm going to have the human make prediction on an example from it. Then I'm going to inform them that this point actually belongs to a bigger region, and this is its description and statistics about that region. So in a randomized study on that object detection task, we evaluate the human performance without AI, so that's at 78%. AI performance, and it's roughly equivalent to human performance at 79%. A human and AI baseline where the human has access to the AI, but we don't tell them, they don't go through this teaching process. They just have high-level information about the AI, its accuracy, specific subcategories that it performs badly on. So that's at 77. So that's really not statistically different from the human or the AI. And now we have our teaching kind of method where we sit down the human first, have them, interact a bit with the AI. We're using our procedure, and it boosts performance by up to 5% from that baseline. And so we have also other baselines where they sit down and interact with the AI, but without the specific guidance from the regions. And the claim I want to make here is that really teaching improves the performance of this human AI team when the decisions from the AI are not easily verified from the AI. So if the AI is just telling you, yes, I think there's something with 90% probability, but you can't verify it, then this kind of very descriptive analysis of the AI model really helps. So I'm going to move on to the final part of my talk, where we think about humans delegating subtasks. And in this final part, I'm going to ground myself in a specific application, which is GitHub Copilot. So if you're not familiar with Copilot, Copilot is essentially a large language model embedded into your code editor. And every time you pause your cursor, the language model is going to generate a suggestion in line in your code. And you can accept that suggestion by pressing tab or rejecting it by continuing to type or pressing escape. And this is really a model used by millions of people on a daily basis. And really, I can, take the interaction of Copilot and put it back into my picture that I've been using. And essentially here, every time the user pauses their cursor, they're implicitly sending a request to the AI. So the model, every time you pause, like if you're working in this environment, you're sending a request to the AI every time you pause your cursor. And so you're getting these suggestions. And now you can either decide to not delegate, essentially reject that suggestion and continue to write code, or delegate by accepting that suggestion and then the AI's code is inserting your editor. So that's my loop here. And the trick is the AI can either send a full code or can say nothing. And essentially Copilot is really nothing more than this large language model and this mechanism to know whether to send nothing or to send a suggestion. And I'm going to show a video of how you could, if you were to build Copilot naively and just, spit out suggestions every time the user pauses their cursor, you get something very annoying. And so you really can rarely write because you're just getting bombarded. So you really need a careful design of this. And so this is a second type of design where you only show a suggestion if you know the programmer will accept it. And so here I'm writing my function definition. And then after I finish writing it, and I've paused for a bit, the AI can show me a suggestion. And so that's kind of a neater way. And I can kind of go from this type of design where I'm just bombarding people to this kind of nicer design with this nice continuum. So the mechanism for displaying suggestion is going to depend on the predicted probability of you delegating to the AI. So I'm going to predict the probability that you will say accept, essentially delegate, given the context of your code and the suggestion itself. And I can threshold that to a probability tau and essentially go from this picture to that video by changing the threshold accordingly. And in practice, the way you would design this is not generate suggestions every time and then decide to hide them. You could even try to predict when you would even want to generate a suggestion. So you first predict, in fact, whether given this code the user is writing, should I even generate something? I first decide whether I should generate something. If I decide to generate, then I decide whether I should show it. And if I decide to show it, then it gets displayed. And essentially, these are based on predictive models of the user's delegation decisions learned from past telemetry of people interacting with Copilot. And these are really very fast models. So in your editor, there's actually a logistic regression model just running on your code with some simple features. There's even more complex models were built like using XJBoost and a bunch of features to work a bit best, but latency is really key here. And so really we're learning from these delegation signals. And there's a bunch of, hypothetical theory of how do you set the threshold, which in theory, you want to think about it of in terms of reducing the user's time. But in practice, that's not what we're going to do. We're not going to use any theory. Instead, we're going to look at these graphs. So that's going to be the last slide of my talk. And so here, this line is obtained by varying the threshold tau. So when do I display the suggestion based on the predicted probability of delegating? And this x-axis is from the suggestions I hit from the user, how many of them were rejected? And the y-axis is how many suggestions do I hide? And so I can kind of neatly go along this line and choose a nice threshold for me. And so, for example, I can hide 30% of suggestions that get shown to users while guaranteeing those that I hid from the user, they would have gotten rejected with a 95% probability. And so that's really retrospective evaluation. And a simpler form of this model is kind of deployed into Copilot. And so there's really open challenges there. Instead of learning from these myopic accept decisions, can I learn from long-term signals? How do I even set the threshold in a sound manner? And much more. And so really the main takeaway of my talk is by having this formal modeling of the human AI team, we can identify inefficiencies in interaction and try to remedy them. And really the most productive avenue has been for me to frame things as a kind of a machine learning problem and try to optimize the AI and user interface side. So thank you so much. And kind of this is a slide with all the people who have done this work. Thank you.
One, maybe two questions. If one has a question, so maybe that's a high-level question regarding this human AI team. So some papers may say like, for a lot of tasks, it is impossible for a human AI team to achieve complementary performance. And the main reason why you want human in the loop is because like for a doctor might observe something that AI does not have access to. So it seems like for here, for example, your second paper you were talking about, it seems like this is in a regime where human and AI have information theoretically the same information access to the same data. So I wonder, like, it seems like from your experiment, like the features that you make decisions whether to delegate, those features are sort of learnable by an algorithm. Like, what's the philosophy behind like you still want to have a human in the loop without like improving an algorithm to make it a stronger one, like dominates human on that data set?
Yeah, that's a great question. So the question was, in the second talk, why, the human seems to observe the same information set. So the paper, it's a bit more general to include Z, but even in the setting where they have actual information set. So, there's a practical consideration that AI is still not perfect in a lot of domains. So you still benefit from doing this smart delegation.
Are you saying, is it like basically computationally harder for AI to learn this additional information, like the information that makes delegation, instead of just letting the AI learn that information and make a decision directly?
So in those settings, really the medical setting, it's really the bottleneck is human trust and automation. So at least for now, we cannot just automate things because doctors don't trust them. So we are restricted to that type of workflow and have to live in that type of workflow. And then once we're in that workflow, we're just trying to do our best. And that's kind of what motivates all of this work, essentially. But in the future, you could essentially just have AI try to delegate things. But then in the other setting where the human observes extra information, informationally theoretic, like you still benefit from, some form of conditional delegation stuff.
Thank you.
Thank you.
One quick one, and then I'll try to be quick. This is low level, but I think related to the previous question. So I'm trying to understand this delta, and delta is strictly positive, if I understand correctly. So I wonder if if AI and human have the same hypothesis class, the model class, why can't the AI model just learn a human model because it has perfect access to the human labels? And in this case, the gap is 0.
Oh, in that setting, maybe I should have clarified a bit more. So the human, I'm not assuming is in any hypothesis set. The human is essentially, to me, just any kind of predictor that could be essentially Y. So here I'm only restricting the hypothesis class of the classifier and the delegation mechanism, not of the human. The human is still arbitrary.
But if the AI class is the same as a human class, like is there still a benefit?
No, there's not.
Okay.
Essentially. Yeah. You could just learn. I mean, actually there's still a benefit because if that hypothesis class is not sufficient enough to express the ground truth label Y, maybe you need a mixture of two hypotheses to express it. So you still benefit from this mixing of the human predictor and the AI's predictor. So even in that setting, you would still benefit. You would benefit more from a joint procedure even.
Great. Well, thank you so much.
Thank you.
All right, so our next speaker is Jan Vies, who's an econometrician, visiting us from the Operations Information and Technology Department at Stanford GSB. He works on high-dimensional and robotic causal inference and data-driven decision-making with misaligned objectives.
Thanks for having me. I'm just taking one moment to get set up so people on Zoom can see this. And the audio is not to my computer, right? That's correct. So it's great.
You can.
Yeah, I'm gonna. right, thanks a lot for having me and thanks for putting together that program. Really enjoying being here. So I'm presenting some work that is joined with Bryce McLaughlin. Bryce was my student at Stanford GSP, is now a postdoc at Wharton and is on the academic job market this year. So the work that I'm presenting here is very much motivated by the increased use of algorithms in high-stake decision-making, which may not be a surprise to those of you who have found their way here, including algorithms being used to diagnose diseases, algorithms setting bail in courtrooms, or algorithms hiring employees. And I mean, that has led to a fast-growing literature across fields. And so I should disclose, I'm more an economist and econometrician working in an operations research group. Bryce is an operations research person. So basically an interdisciplinary research agenda that includes people from computer science, but also from statistics, operations research, economics, about how we can train algorithms in those contexts of high-stakes decision-making, how we can optimize resulting decisions, and also how we can address issues with bias in the training data or bias in existing decision-making. But at the same time, the picture I've shown you here, of course, for those of you coming to the specific workshop here, seems to be very misleading, because in all of those three cases, it's not really the algorithm taking decisions. So I would argue it's really a doctor diagnosing a disease with the help of an algorithmic assistant. It's a judge setting bail with the help of some risk assessment provided by an algorithm, and it's a manager deciding who to interview, who to hire based on some information provided by an algorithm. And so for me, that raises the big question, like relative to a world where the algorithm is taking the decision itself, how should we think differently of how we should train the algorithm and what its consequences are? And specifically in the talk today, I'm presenting just one specific example, how we think about how algorithmic recommendations may affect decisions, and therefore how we should think of their optimal design. As I said, I think it's a part of a broader agenda across fields that's really at its core about what the comparative advantages, comparative costs of those two are and how we can best put them together. And so in order to take a stab at that today, I will be in a framework where I'm just taking as given that the human is going to be the final decision maker. And I'm going to ask the question how we should design the algorithm in the background. So I'm not going to necessarily talk about questions of delegation and which decision should be taken by whom, but I'm just going to assume I'm in one of those contexts. All right, so when I'm in one of those contexts, I really see two roles of the algorithmic recommendations. So let's think of, say, a doctor who has some data about a patient and an algorithm that helps interpret that data by, for example, providing some risk assessment of what kind of diseases. And I would primarily think of this as providing some additional information. So it allows the decision maker, who's a doctor here, to update her beliefs based on this additional information. But I would argue that that's not the whole story, that in many practical cases, that these recommendations do not just affect downstream information, but that they may also affect downstream preferences. So let me give a very concrete example for a doctor. So assume there's a doctor and the doctor receives a high-risk assessment for a patient. That doctor, even if the doctor has some private information that makes her believe that this is not really a high-risk case, may actually be reluctant to overcome that suggestion because she may be afraid that if later on that patient actually turns out to be sick, then she may be sued or that she may get pressure from the person she's working with. Similarly, if you think about a judge in a courtroom who takes a decision of who to jail or not, if that judge receives a recommendation by an algorithm to jail somebody, even if they think that they know better because of their private information, they may be very unwilling to overcome that recommendation because it may look very bad if they release somebody who then later on commits a crime against that recommendation. So what I'm arguing today is that one feature of the interaction between algorithms and humans is that we shouldn't just think of the information, but also of how it checks preferences. And that's a phenomenon that in that paper today, we will call recommendation dependence. And so what I will argue in the next half hour or so is that recommendation dependence creates some inefficiencies where the decision maker is overly responsive to the recommendation. That in response, optimal algorithms should be less conservative in their recommendations, kind of anticipating that. And that specifically, in some cases, remaining strategically silent. So deciding in some cases to not give a recommendation may actually improve outcomes and may be one of the keys in order to achieve human AI complementarity. And also that like some theory from economics, specifically economic psychology, specifically prospect theory, so the systematic theory about reference points and how they affect decisions, may be helpful in providing some structure and microfound what I'm showing you today. Yeah.
Question, when you say it shapes preferences, that's not the same as like shaping like the scoring rule that they think they're being judged on, or is it?
So you can think of this way. So what I'm thinking about here as preferences is basically the revealed preference. So I'm assuming that I'm rationalizing what the agent does in terms of what kind of losses they put what kind of weights on. And then you can think of that basically this would change the weights put on specific errors that they can make, and therefore how they evaluate it. And I think there are kind of two interpretations of that. This last point here suggests a psychological interpretation that in my mind, kind of some losses relative to some reference points may loom larger, but I think it can also very concretely be related to how they feel they evaluated. Like if a judge at the end is evaluated by the quality of the cases, or a doctor is evaluated by how well they did, there may actually be a component where I'm looking at cases where the doctor went against the recommendation and then would actually punish them for doing that.
Thank you.
Sure.
A quick question. Yeah. So here the only player or agent is this person who is choosing whether or not to use the AI's recommendations.
Yeah, so I would think of, so I'm going to come to that in the very end, like the way that I've come to conceptualize this, you know, coming from economics, but also trying to build some bridges in language, is to really think of it a principal agent model, where there's an agent who's the human decision maker. That human decision maker decides what to do. That could be adopting the recommendation, ignoring it, or, you know, taking the information and doing something else. But then I also think of a principle. The principle is kind of the designer of the algorithm. The principal decides how I should design the algorithm in order to lead to good downstream decisions. And now within that framework, we can use all the tools that mechanism design has available to talk about optimal design. For example, differences in information between the two, differences in preferences between the two.
But when you say algorithm, do you mean AI thing or?
Okay, great. So for me, what I will take to be an algorithm here is basically a mapping that takes some features and makes a recommendation based on that. I think there's kind of a bit of an ambiguity how we talk about algorithms. So in the statistical decision tree framework, what I mean here is basically a decision rule. So just take the X, tell what to do. But of course, there's also the algorithm in the background, which is taking training data and coming up with that thing. I'm going to talk less about that. I'm going to talk just about the outcome of that if you want. But that's a great question. Yeah.
And so you're thinking about this recommender being aware that it's changing preferences?
Yeah, so I'm first going to look at a case where we are not taking it into account, and then later I'm going to talk about how should we therefore change the recommendation to anticipate.
And you want it to do well with regard to the original preferences.
Yeah, with respect to whatever the principal's preferences are. So our, you know, desire to jail people who will commit or at risk of committing a crime and so on. Yeah. Okay. Just before I go into the actual model, so this is a very kind of myopic representation of literature, because this is maybe more the view from the operations and economics literature. So you will see that it's out of date in two ways. The first is all the dates are like stopped like 2 years ago, because that's when we originally put on that review. And the second is that it is awfully slim on the computer science side of things. And I think one of the positive things I have to say about this whole area of human-machine interaction is that the positive thing about the literature is that this slide is very much out of date, because so much has happened over the last 2 years. But just like, what's the idea of our project? So what we are doing is we are building models of algorithm-assisted decision-making that kind of integrates ideas from behavioral economics and behavioral channels in order to make sense of some of the anomalies that we see in empirical work that we wouldn't be able to make sense of if we just assumed rational decision makers. And just to maybe pick out one of the studies to make that point, studied by Stevenson and Doliak. So they, for example, study what happens empirically when a system is introduced that assists judges in sentencing. And so they compare what do these judges do without algorithmic risk scores versus what do they do with algorithmic risk scores. And these algorithmic risk scores are basically not just optimized for predicting, well, who is likely gonna commit crime or fail to appear at court. So like not just good at predicting risk, but they're also designed specifically to, for example, reduce racial disparities or to reduce prison populations. So there are a few ways in which we could think of objectives that those algorithms follow. And so what they show is that on the one hand, the decisions that judges take are moving towards what the algorithm recommends, meaning that there is a higher correlation between recommendations and decisions once the algorithm is shown to human decision makers. But at the same time, that some of those quality of decisions that we may care about, like what is the risk of the released population, what are prison populations, or what are racial disparities, don't actually markedly improve. Meaning that from a purely rational perspective, I would have real trouble explaining what's going on here, because I would think like providing more information to the decision maker can kind of only improve the outcomes, unless I believe that this is really about misaligned preferences. So what we are trying to do is we're trying to build models that show what some frictions could be in why we don't achieve that complementarity and what some consequences are for the design.
But couldn't it be another explanation, a rational one, that the judge changes their information acquisition policy in response to having access to AI? So they think about different facts, they search for different data.
So I do agree with you. I think there is more to be modeled here. So for example, you're suggesting that something might be interesting is that I now give you more information, so maybe you have less of an incentive to search more deeply. I still think that on the margin, giving you that information should still lead on a margin to an improvement in decision quality. At least that is like, I mean, we could think about assumptions, but I intuitively find it hard to justify a model where I give you more information and then you search so much less that the resulting information is worse.
Yeah, but it's multidimensional decision, right?
I do agree it's multidimensional. So I do think I don't. There's one thing I don't want to claim. I don't want to claim that that mechanism I showed today is necessarily explaining a specific empirical case because I haven't done that analysis. But I think it's one part of the puzzle to think about frictions where there is kind of a non-rational response. And so I agree with your point about search costs. Is also one direction that we're currently evolving this model is kind of being more kind of microfounding a little bit more what could be going on. I think the idea that if I give you some recommendation, it may actually mean that you have to search less. And in the complementarity information, you may be able to more quickly decide a simple case is actually an important factor that is not modeled here today, but that may be interesting to model more. Okay, so let me just give you the general setup, and then I will jump into the very concrete, simple example and refer to the paper for more general theoretical treatments. So what I'm assuming is that there is a decision environment that corresponds to this distribution over available information, a public signal about a specific case. So the case you could think about is a defendant appearing in front of a judge. The public signal is something that would be in their file that both is algorithm readable, meaning I can make a recommendation based on that using an automated rule. And it is also human available, so the human could look it up. But then I'm also assuming that there are potential information theoretic reasons for why there could be complementarity in the information space here. So there is a private human-only signal, so that could be the judge deeply looks into the defendant's eyes and exactly sees what's going on, or maybe in a bit more benign way, the judge can ask some questions and get some additional information that is not in the file. And I'm also assuming that there may be some information that only the machine has access to. And I think here that really would require, as you suggest, a little bit more microfoundation, but it could be that there's a very thick file. The human is never going to read all of it. The machine is able to read all of that, or that the machine is able to automatically pull in some additional information. You could also think of this as a signal about the training data so that the machine is able to, in a much more systematic way, extract information relevant to this case from large training data. Then there is a label. So in this case, everything is as simple as I can make it, which means that there's only outcome that is bad or good. So that maybe defendant failing to appear at the main trial or committing another crime would be a bad outcome. Them reappearing, not committing another crime would be a good one. Okay, so now I really have two players in this game that I'm thinking about. The agent I'm thinking about is a decision maker who takes a decision of whether to take a safe choice. So safe choice would be jailing somebody, or a risky choice, which would be releasing that person, where the idea is that in a good case, so good outcome, I'm okay to take the risky action, but in a bad outcome, I really want to make sure to take the safe action. That person does that based on observing the signal X, which here I'm just conditioning on. So think of this as we've already conditioned on X. We've agreed on what the X is, so therefore I'm going to drop it from the model from here on. Then their private signal H and a recommendation, which is going to be an interpretation of the signal available to the machine. where the mapping from the information available to the machine to the recommendation that is being made is going to be what is specified by a designer, or what you can think of as is the result of some fancy schmancy AI algorithm that the designer runs in order to provide information. And so crucially, I'm assuming that these two players in my game here may end up having different loss functions. So the designer cares about some risk that expresses the cost associated with taking action A when Y happens. The decision maker minimizes decision loss when with some alternative L star that later on I will introduce to also include potentially reference effects, which meaning that their loss, so the way that I can describe what their preferences over choices are, may also include the value of the recommendation itself and is not purely consequential list with respect to the realized outcomes. All right, so that's our general setup. But I'm now gonna start first with the aligned case. So in the aligned case, I'm assuming that the losses are the same for both. So in this case, I'm assuming there's some type 1 error if you take a safe action in the good case. So that means you're kind of being overly prudent. You're making a mistake because in the good case, the risky action would have been good enough. So that would be jailing somebody who does not end up committing another crime. But then a second cost that I think of is generally the most salient one here, which is a failure to take a safe action when something bad happens. So that would be the judge releasing somebody who then continues to commit a crime or fails to appear at trial. And then I'm normalizing the cases where I do the right thing to 0. So, okay, so now assuming that we are interested in minimizing expected loss in this case. And for illustration, I'm really taking the simplest possible case to allow us to talk through what the structure of such an exercise could look like. So specifically, I'm assuming that a bad outcome is realized whenever the combination of the machine and the human decision indicates so, and does so. The color isn't particularly vibrant. Let me just check whether that's me. No, okay. So whenever basically the sum of the machine information and human information, which here both I'm assuming are just numbers between 0 and 1, whenever that is larger than 1, then the bad thing happens, and whenever it is smaller than 1, the good thing happens. So what does this mean? This would mean like somebody who has perfect information here, knows both the machine information and knows the human information, could always take a perfect decision by just adding the two up. Of course, this is super stylized, just to get some clarity here. But I now want to use this model to talk through what a human would do on their own, what a machine would do on their own, and how I should optimally combine those two. So first of all, what would a human decision maker here do? Well, a human decision maker would only observe age. So all they could do would take a decision that differentiates based on the age information. Intuitively, if age is very high, they would want to take the safe option because that means there's a higher probability of the bad thing happening. If age is very small, they want to take the risky decision because it means that the good outcome is more likely. Here, I'm assuming that the costs are so that it is more costly to take the risky decision when something bad happens. So therefore, I'm more prone to taking the safe decision. And in that case, I obtain some costs where I'm doing the safe decision, but the good thing happens, I pay some cost C1. For the opposite, I get some cost C2. And I would now choose this threshold to basically minimize the areas multiplied with those costs. So because I'm assuming that the type 2 error is much more costly, that means I would try to make this left top triangle here smaller. So what does the human do? Well, they choose some threshold. In this case, they choose a threshold that is equivalent to the probability of the bad thing happening conditional on the information being equal to the ratio of costs. Well, in this case, costs of the type 2 error normalized by the sum of the other two costs. So of course, this is imperfect, right? Because there's a lot of mistakes happening, which are those dark areas here. The machine by itself, if I just use the machine, of course, would do exactly the same thing, but cut by M rather than by cut by H. And so neither of them would do particularly well here. And the hope is that we can put both of them together in order to get to a better decision. So let's think about how that would look like. I'm now making the assumption here that the machine is simply providing a recommendation of taking the good or the bad action. Of course, that's a restriction. You can think of it as a restriction to the complexity of communication. I'm later going to talk a bit about what happens if the machine gives a full scoring. But like, let's assume the machine can only give you a binary signal and either say, oh, I recommend you take the safe action, or I recommend you take the risky action. So in this case, the human now knows something about where we are in M space. The human will know whether we are in this higher risk area up here or the lower risk area down here. And depending on that, we'll choose two different thresholds to minimize overall loss. And therefore, we'll end up with overall much lower losses because now all the mistakes I make are as kind of these dark triangles and adding up over them.
Sorry,
So,
just to
yeah.
clarify, here the utility of the decision maker depends on the AI's label of the message or the meaning of the label.
Okay, so great question. So right now I'm assuming that our two losses are fully aligned, so there's no reference effects yet. When I learn from the AI that the AI says, oh, it's risky, what I really just learned is that the M is up here. The fact that the AI calls this risky so far doesn't play any role. It's basically just the AI tells me I'm in region 1 or I'm region 2. We're assuming that we all know this distribution, so this is why I can take this decision. Later on, it's going to matter how these things are labeled because I'm going to assume there are going to be reference effects with respect to that.
With respect to labels.
With respect to the labels, yeah. Right now, the labels basically are just a partition of or like a filtration of the space if you want to. Yeah.
Well, in some sense, these are both independently distributed, right?
Yeah.
So I mean, can one interpret what's happening as you're just getting extra information because these are two features which are independent and giving you something about.
Yeah, so in this case, basically, so the way that I want to think about it is I'm only focusing on the orthogonal part of the information. I also had this joint information X. So the way that I think about it is that X includes anything that is joint information between the two, so that I could choose kind of M and H to be only the orthogonal information that is independent on the margin. Because if there was some joint information in that, I could put it in X. So I don't have a formal statement of that, but I'm thinking of those being the independent information that the two have after I'm conditioning on any joint information. But that means that I'm assuming of those as being complementary and additional information. So this is why I can draw a nice square here where these two are independent. I think it would be interesting to think through more if you think that they are correlated. And maybe separately think about what the human believes to be the case. But like here, I'm just assuming the human knows what's going on. I'm not sure that answers the question.
No, I mean, I guess what I was wondering is, it sounds like the advantage you would get if you have two samples as opposed to one sample from the same distribution. Right, so
I see. So can you say a little bit more? So
there is some distribution which which is the distribution you get after conditioning on X.
Yeah.
And then you have two IID draws from the same distribution. So that should give you more than just one IID draw from the distribution.
So you mean IID? So you mean a draw from H and a draw from M as the two draws?
In that case, they were IID. So
yeah, so that's true. Like they're both ID, and like I agree with you. Like the idea is like if I can use both information, it improves things. So that's by design here. I do agree with that. I mean the fact that they are both 0, 1 IID, I think it's just a design choice here, right? It could also have been that the machine decision is some like 5 different values, and this is a continuous one. But I think in general, the idea here is that yes, like I think there are two things that are both relevant for the outcome. I want to combine them. I'm assuming that there is some limitation to how much the human will be able to understand from this complex machine signal. In this case, I'm assuming for the human to use it, it has to be collapsed down to either good or bad recommendation. And then I'm asking how to do that optimally. Yeah. So just wanted to point out a first maybe trivial thing is that the optimal recommendation that puts things here in 2 actually looks different from what the machine would decide, right? Like the optimal recommendation is not the same as the machine telling this is what I would decide. Because in a way, the optimal way that the machine creates a recommendation is really about maximizing the information that is still contained from that first stage. In this case, it turns out the way of maximizing the information about M is not to cut it kind of where the machine would cut it if it was taking a decision, but instead by doing it 50-50, like maximizing the information included in that one bit of information. So yeah, just like keeping track of this a little bit, like we have this as a general statement as well, like the optimal recommendation here is different from the optimal algorithmic decision, even in the baseline case. where there is alignment between the two. But now I wanted to get into the meat of my presentation today, which is thinking about that there could also be recommendation dependence, where in this interplay, we are now assuming that the loss that the decision maker will experience, or the loss, if you want, that they take decisions according to, so I'm not really taking it as a step where there's a psychological description, is like the loss that is revealed by the preferences, by the choices that the decision maker makes, that loss has an additional part. Here I'm adding the following structure. So I'm assuming it's the same loss, so the same type 1, type 2 errors that the principal cares about. But then there is an additional aspect from deviating from the recommendation by the machine. This may look a bit complicated, but it's really very straightforward. So this loss is only non-zero if the action A is different from the recommended action R. And then it can go in two ways. The first one is that the recommendation is take the safe action, but I go against it to change the risky action, and then something bad happens. That's what I really think of the salient thing. This means a judge sees that this is a high-risk applicant according to the algorithmic recommendation, decides to override that and release the defendant, and then that defendant commits another crime. There could also be a second way of going against the algorithm. The algorithm says this is a safe defendant. The algorithm says this is a risky defendant. I decide to take the safe, I think I may have messed this up. So the top one here should be that the recommendation is to take the safe action, I take the risky action, right? So here it could be that the recommendation is, sorry, this is correct on the slide, but I got confused. The recommendation is to release somebody. I decide to take the safe action. I don't trust the algorithm. I want to be more prudent. And then it turns out it would have been a good person. Now, that second one in this case would be less salient. I think you could see that for two cases. Maybe it would be seen as the less problematic cause. But second, it may also just not be observed to the public, right? I don't actually know what would have happened to this person had I released them. So I may never be able to find out that it was really unnecessary to jail them. And so if I want to add another example, then these costs could also be the cost of being overly safe in ordering an unnecessary test against the recommendation in a medical setting. So the algorithm says it's not really necessary to run an extra test here, but I want to be prudent, I order an extra test. While the second one would be a cost of a risky mistake where the algorithm says, oh, there's a risk of some disease, and I, as the doctor, think I know better. I'm not ordering a test, and then I get in trouble if later on somebody actually turns out to be sick or turns out to be having needed an intervention. Okay, and I'm now going to ask the question, if I add this additional cost, how does this change the view that my algorithm operates and how I should design it? And so in this case, let's assume the case where there's only an extra cost delta 2. So I'm ignoring that cost of being too prudent, and I'm just focusing on the idea that there may be a large cost associated to me taking a risky action against a safe recommendation. So this is the judge releasing somebody who's labeled as risky. So in this case, what happens? Well, in the eye of the agent, what happens is that the cost of a type 2 error in that risky state here has increased. I'm now taking an inefficient decision where I'm too prudent when the algorithm gives me a safe recommendation. As a result, I would want the algorithm to be less conservative. So we are now making excess mistakes up here because we're making too many type 1 errors. If I now think about how that should affect the algorithm, then one response is that the algorithm should make the safe recommendation less often to counteract that potential bias. And if I do that, then the decision maker also adjusts their thresholds in both of those areas, which is efficient down here, continues to be inefficient up there. But overall, the amount of errors I'm making are slightly lower. So first takeaway here is that if I have these recommendation-dependent preferences, then that affects decisions in a way that become inefficient because the agent is now overly relying on the recommendations and following, in this case specifically, the recommendation to do something safe too often. So what are potential ways beyond adjusting the threshold that I could do? Well, a second thing that we analyze in the paper that can generally help and argue formally in which way it can is that we could also add a third level of recommendations. Now, in a way that is cheating, because of course, if I allow there to be additional information and I'm giving you 3 rather than 2 different partitions of the space, then of course, that just provides additional information. But we are assuming that that third level is effectively one of the algorithms saying, I don't know, like you should take the decision yourself without taking my recommendation into account. If you now assume that this third level does not induce any recommendation dependence, because there is no label provided in this case, then I have 2 types of benefits from doing that. Not just that I get increased information, but I'm also able to avoid recommendation dependence in this middle part and therefore get a double benefit. And so what we show in the paper is that that basically in general can lead to complementarity, but it's also related to some empirical work that uses similar things in the context of doctors. So one place where we found that is a study on sepsis risk prediction, where the researchers here add an indeterminate prediction to the cases where the algorithm is unsure about sepsis predictions and show that this is key to achieving complementarity between human and AI. Yeah.
Just to make sure I understand what's happening in the pictures and
sure.
The kind of recommendation dependent preference you're thinking about. You're thinking that if we disagree and then the human's wrong, that's sort of worse for the human.
Yeah.
And probably both sides. So, and those are the most extreme, I think, wrong triangles here. It's the red one at the top, and it's the blue one at the very bottom, right?
Yeah, that blue one you would also.
And in your previous figure, when you only had good and bad, there's a trade-off between whether you favor one or the other. Because if I move my line up, then I go down, and then I get this one at the bottom bigger.
I agree.
Right, so I make that bottom one bigger, and so you have to trade off the 2. But when you add this middle region of don't know, you can actually.
Yeah, you can. Okay, so great. So first of all, I fully agree with your point. So the point about these recommendation dependent preferences is that now some errors are looming larger than they should. And those are the errors where I go against the algorithm. I'm not saying that I shouldn't care about a type 2 error, but I'm now caring too much about a type 2 error in the world where the algorithm has suggested to take the safe action. And similarly, you could be worried that this one is also higher. So normally what I would have a trade-off where I'm now thinking about where is this distortion larger? And then I'm reducing the recommendations that are associated with a larger distortion. But I would have to trade off those 2 distortions. Adding this third level does not only provide me more information that I think is still in a way that a human would understand, but it would also allow me to kind of break this trade-off by saying, what I really want to do is I want to expand the area where I'm not giving recommendations on the margin. So relative to a rational baseline case where I'm just giving 3 different levels, I would now want to give that don't know one more, which of course is under the assumption, which gave me a lot of leverage here, that withholding a recommendation is not going to induce a reference effect. So that's the idea of this specific construct. I'm not sure where in time, how much more I have.
I think you have 5.
Okay,
7 minutes.
7 minutes, great. So, okay, just wanted to collect kind of the main results here. This may look a bit gimmicky in those pictures. We have some formal statements that put that into a more general model in the paper, where kind of our main arguments is, first of all, I already told you that optimal recommendation is different from thinking about an optimal decision. Second, recommendation dependence increases adherence in an inefficient way. So our hypothesis here is that by making these suggestions, you're making decision makers that have a lot of private information follow them, even in cases where their private information indicates otherwise. Giving recommendations as a result in general can make things worse. So there are cases we can construct where giving a recommendation will always distort more than it will help. Of course, these are cases where the human has a lot of information and a recommendation isn't very complementary to that. But if we instead allow for strategic silence, then we can show that it's always possible to choose that in a way that it guarantees complementarity. So we cannot show that complementarity is generally possible in a world where we just give binary recommendations, but we can show that allowing for a don't know one within the class of our preference is always possible. The argument behind it is not particularly complicated. You can show that we can do better than just letting the human decide, because you could always just send don't know. And then we can show you can do better than the algorithm by itself would decide, because in that case, the recommendation dependence is not actually a problem. So if you're over adhering to the algorithm, you're not going to do any worse than the algorithm by itself. And so putting those pieces together, we show that in a more general model. But what I want to end up in my talk today is kind of making two other connections that I think could be helpful for the broader community, like what kind of tools can we actually use. I started out here with a very ad hoc model. I said, it's intuitive that errors that I'm making that going against recommendations are more costly, but we can tie that to one of the most celebrated results in psychology and economics, specifically prospect theory, which makes the claim that choices in general can be systematically deviating from rational choices in two specific ways. The first one is reference dependent, so it matters what your reference point is relative to which you evaluate an outcome. And the second is relative to this reference point, you have loss aversion, meaning relative to whatever you think the expectation is or the reference point is that you had assumed, getting it wrong, like achieving loss, is like more costly than the benefit you can get. And so this is like a general theory that is used to make sense of some systematic deviations from rational choice. And so I could write this up in my case. I could write prospect theory preferences where I'm using the loss under the recommended action as my reference point. And then I write my loss if I take my action relative to that. But now I'm putting a larger weight on a negative deviation in loss relative to the reference point, relative to a deviation where my loss is smaller. So on the left is the case where my loss is larger than if I just implemented the algorithm directly. On the right is the case where my loss is smaller if I directly implemented the algorithm. And if I write this down, then I get exactly the losses that I had. So I can microfound that by combining prospect theory in this exact way, where now basically the additional losses that I experience will depend on the degree of loss aversion. And the higher the loss aversion, the more additional loss I get if I deviate from the algorithm. So that, of course, depends crucially that I'm making the reference point here, the recommended action by the algorithm. But I think in many cases, that's a realistic view of seeing this. So the second thing I just wanted to mention is that I presented an example where the recommendation was given by a binary recommendation. You could also think of a case where a full risk score is given, like the judge may not just receive a recommendation, jail or don't jail. The judge may instead receive a recommendation that is implicit to a risk assessment, like what is the probability that this defendant will fail to appear or commit another crime. And so if I do that, like in another example we have in the paper, you can still assume that there's recommendation dependence, for example, because there may be implicit recommendations encoded there. So I'm assuming that the decision maker thinks that a high risk assessment is an implicit recommendation to jail, a low risk assessment is an implicit recommendation to release. So in this case, we still achieve inefficiencies in such a model where if I'm when I now have kind of a continuous probability distribution of the outcome rather than this binary one from before, when I now receive a risk assessment that is very high, I may err on the side of jailing somebody. That still leads to inefficiency, and I can still improve that by choosing an area around the threshold where the algorithm is unsure what to do. So in the area where an algorithm would not know whether to jail somebody well or not, where withholding that number altogether, so basically replacing, hiding the risk assessment, would still lead to an improvement because I'm reducing the amount of errors I'm making. I'm basically allowing, in this case, for some more type 1 errors in return for costly type 2 errors. So what I'm saying is that I think that story is easiest to tell in the case where the recommendation is just a binary thing. But the idea that there are recommendation-dependent preferences, as well as the idea that hiding information may be valuable, we also model in the case where the assessment is continuous, and we may want to hide that for specific cases, which I think is a realistic case in some cases. So let me first summarize and then conclude on kind of the more broad agenda. So what do we do in this specific paper? In a model with binary outcome and binary recommendation, and then a decision that is taken against that. What we show is that the optimal recommendation is not the same as the optimal decision. That ignoring recommendation dependence effect yields inefficient recommendation thresholds, where generally you're kind of not anticipating correctly what mistakes humans make. and that the second best algorithm provides less conservative recommendations, and specifically there is an additional benefit from incorporating strategic silence. So basically in this class of problems, we would expect that sometimes withholding recommendations is actually part of designing a successful human AI collaborative system. And then we can motivate some of these things from behavioral science, which I think is just a nod to the fact that we have a lot of tools available that allow us to model the human. So I think we should go ahead and incorporate that in our AI systems. And I'm ending on just teasing a broader agenda. So this is with my student Bryce, who now postdoc at Wharton and currently on the job market. So if you're looking for somebody doing smart things in this area, what is our general approach here? So our argument is that in a lot of, especially the kind of more applied literature here, there's been a lot of focus on this idea how an algorithm can take good decisions. Like how can I train an algorithm to take good decisions about credit scoring, about who to release from jail? But then in many cases, the real structure looks more like an algorithm giving recommendations to a human, and a human then takes decisions. And that really takes modeling the human decision maker in order to make sense of. And so what we do across a number of our papers is basically taking a principal agent model where there's a designer who designs an algorithm and a human decision maker who's the agent. And we're really thinking about this as a principal agent model where we ask the question, what kind of design decisions should a principal do in order to affect decisions by a human in a positive way, assuming there can be frictions. There could be asymmetric information, there could be different preferences, there could be effects like the ones I showed you, which are reference effects. And so we've done that across a number of papers. We've asked the question how that should change views on what a fair algorithm looks like. Like, how should a fair algorithm look like if I don't care about the fairness of the prediction itself, but I really care about the fairness of the decision? How should we deal with reference points, which is this paper? And then Bryce's job market paper kind of takes a causal inference view and says what we should really care about is kind of potential outcomes that show how a decision is affected causally by a recommendation, and we should use that framework to make sense of good recommendations. So if you're interested in that, all those papers are on archive. All right, thanks a lot. Yeah.
Can you give a little intuition about how you would extend your model to, say, multiple outcomes, not binary, and the counterfactuals that you might not observe, given that there could be multiple choices that where you take a single choice if you don't observe the outcomes of the other choices?
I see. So you're basically okay. So to kind of frame your question, like what I've assumed here is right, basically perfect information. I know the full distribution, I have a single outcome. So the two extensions you're thinking about, the first one is having multiple outcomes that may matter, and the second, I'm not actually observing the outcomes under all the different counterfactuals. So for the latter one, what we are doing in this paper is we are basically saying this is like a causal inference problem. Like we have potential outcomes. We only really observe the outcome under the thing that was recommended. Can we use some tools from in this case, the type of things that econometricians do when they analyze instrumental variables? So the way that we analyze causal inference, put some assumptions on it. For example, maybe that the recommendation is only going to shift you in the way of the recommendation and not in the opposite way. In order to then say, what are some reasonable rules that are still second best if we have limited information? Or how can we design an experiment to learn over time? So I think my quick answer to that is, unfortunately, I think theory is limited by itself to answer questions of how to define optimal recommendations, because we have to learn not just about the relationship of features to the outcome, but we also have to learn about the relationship of recommendations to human decisions. That link is inherently one where we need a combination, I think, of economic modeling. But honestly, as an economist, I can say that our models of human behavior are also very limited. So it's inherently an empirical question. So the way we approach it is to say we should think of this more as a bandit problem, where we are trying out different things to not just learn about the relationship to the outcome, but actually learn about the relationship to the human decision. That's a bit of a cop-out. It kind of just says, I don't know, but we should learn it. The question of having multiple outcomes that are affected is an interesting one. So, I would think of this as, can we write this as a utility function? And can we somehow get a grasp of what we think, what the utility of the agent looks like and what the reference points are? But I haven't thought about this, so I don't have anything smart to say. Thanks. Any other?
Why don't we take a coffee break then? Someone coming back?
Yeah.
Okay, yeah, so 20 minutes. Back to 11.
Let me send you this. You just give me your email address and then I'll write it off.
Oh, nice. That was pretty good so far. I don't know. Did you get your beginning? What are you working? What are you working?
Yeah, we're trying to focus on each.
He's like more like operations research, operations management. I don't know which area you do this. Oh, no.
Yeah.
No. Operation guy, or you do something.
Yeah, because like my yeah, exactly. But yeah. That would be I can send you the program. Yes. And otherwise, maybe the other people who can manage. Thank
Yeah, one question, knowledge question.
Yes.
The first
Exactly. Human doesn't forget, so I'm trying to make sure all of the.
Is that your going page?
Yes. We had thought about that. Interesting observation.
So, do we have like three studies do on question answering and one?
Decision to let it go or not.
Yeah, there's this across the river, so.
Are you?
Yeah, the question takes a lot, but each task like requires different teaching. Like.
That number I made up.
So probably. And so, yeah, at the basic, I've been saying that some leaders like this. You cannot verify. So in that context, actually, the main like because the emissions are so sensitive that like I know there's traffic lights, you have no idea where, but we don't allow small like if the
right.
So because you basically think of this as sentencing guidelines as being the recommendation.
you don't like maybe it's
What if they go severely below?
You get that.
In a lot of.
If they are right. Or they tell you,
So
I don't know what the answer is.
The standpoint is 70%.
Then you don't benefit from it. If they lie, it's already giving you enough.
But you've already studied that. Sorry.
Well, I was just saying. I can see you're expanding your model.
Yeah.
I don't think that, whatever, there's not anything.
Knowing that this is 70%.
So waiting for.
Definitely not required.
Evaluation. Yeah, no, I think it makes good sense.
References. So he said, let one guy, you could let him know. He said, John, I'm Steven. Alex, any question? Let him know it's well, you start knowing.
Yeah.
You see all the videos and then go to the studio, not like me. So, just want to.
Yeah, no, I think whether you see kind of these types of these recommendations as that's like the sentencing recommendation. What are they, you know, specific
Typically, letting some out, model. They are in I think very different. So I look at the paper and then. That OJ line out.
Very good, very good. Yeah, I have to. I'll never get that. Thank you.
Very like agenda, so we can some work on that.
Yeah, so basically, like spatial persuasion.
Right.
Yeah.
I mean, for that, the quantification, which I think is useful, because currently, in the look said, which is that's offering but for example, it's like I think I'm not trying to wait to find that.
Not with integrating information. Philosophy. But model with learning.
And then right designer and then
As a reference point, we are not going to basic reservation page. Yeah, so it's one of these things.
No, I know.
Yeah, so here is it depends on the normal assessment, but you could also look at this. Because then it's not again because you get rid of that there is like it's hard to interpret information.
Exactly. And this I mean,
but I think that's also the weak part. I thought that it's not the situation conservation is the themselves.
I think that is very used by the algorithm. And then you actually see, and then you can calculate the designer. So the designer is a function of the here.
Really appreciate that. By making
But I mean, part of it is just like,
and then
even if I tell myself, I really should go down that far.
And then you can just find out
I could use that as a the one thing I'm struggling with is this idea that the decision maker interprets things not by what it can is the level of complexity where maybe you just have to make additional assumptions that then in the algorithm is not the same or something like that.
I mean, think about also you start to on a regular basis.
So you should
You'll
realize,
understand what
I do agree.
discrimination is like.
But I mean, it's still amazing how much systematic errors we make. We get on again.
So I agree.
But I think like airing that assumption that what is represented in this perspective would be kind of the organization model of the material. What's long and you basically ask the question, of course, there is. I know, but I'm in Boston, so I'm sure. I was on athletic like what's your like top athletes Yes. So loss is like how we can AI. This is a measure of how we
how you can tell from whether AI
have you
yeah, we design your
hi. It's a constellation which really I think creates a oh, you were at the conference? Oh, cool. Yeah, like, it's a good question. Okay, what was your presentation? I forgot. Yeah. Okay, Jason presented it though. Pretty presentation. Okay. I'm busy. Oh, yeah, I think it's very close. Cool. Nice. And your art so you okay. It's this benchmark data set. It's just the
Yeah, strategy at Nickel University. But you know, sort of
so are you where are you? I imagine you're sorry, evaluation of
yeah. Like the rooming area of whether you could achieve that your experiment or like
how are you thinking about that? To your benchmark. I guess your benchmark here.
Yeah. I was thinking here versus like whether human and AI decisions are equal.
Right.
Whether humans are better at the subset of He says our AI are better and another person. And another reason you probably company whether some information AI can have some.
It's like, the way I would think about it, it's some measure of just humans, just AI.
Yeah.
Okay, so you have.
Yeah, but like when we consider like we get together, what are we? Yeah. Well, we wanted to have period.
But it's an interesting. That's
Actually, it's just the human intelligence to decide You're actually doing combined for 3 minutes. Okay, good.
Besides the Asian optical.
Cool, that's the thing about strategy, and then practice to measure how close to that is. What are the sorts of exercises that, what are the kinds of exercises that you have humans and AI? Okay. Yeah. What sort of thing?
Oh, we
But like it's last year more things to do.
Yeah, and it wasn't. It didn't get that from me.
Okay. Well,
Yeah, even there's a lot of power games together.
You know, one of my biggest friends works on this one called
The ranking rate
But it's hard
Oh, yeah. There's not.
No, I was exercise. I was in so it's like my work it's a great seeing these series. My work great and maybe you don't consider these personal experience. Compared to my work. Yeah. I can figure out what to do. But it was giving on the third day. Okay, great.
But I think my research.
Maybe you have to personal. It's on the workshop webpage.
Okay. I should do it now.
Yeah, and then you'll like review yourself and see your audio. So you just be able to share your screen. It's great.
Okay. And the clicker.
Yeah, I'm not sure.
Oh, they are. Because we are not foreign.
Yeah. From USC.
Bring the university to the way.
That's great.
Which is fantastic and very large and complicated challenge.
Yeah. We should get. I know. We have like a lot of, Amazon has like all kinds of.
Time to get started again. All right, so our next speaker is going to be Ming Yin. She's an assistant professor at Purdue University in computer science. Maybe not assistant for too much longer, if I had to guess. Previously, she did her PhD at Harvard with the Econ CS group. She was then a postdoc at Microsoft Research New York, working with the computational social science group. And she works at the intersection of applied AI, ML, HCI, and computational social science. So I've been watching Ming's work in this area for a while. She had some really interesting work, I think, during her postdoc, where she was comparing sort of the impacts of what people experience when they're using some model and getting a sense of its errors that way versus what they are told about the model, such as its, stated accuracy. And she's done a lot of work since in the same vein of sort of trying to understand, how to model a human agent interacting with an AI system, what signals to show the human, how to think about the importance of the human's, confidence function and calibrating that. And so, yeah, I'm excited to welcome her today.
Thank you very much. Well, it's a great pleasure to be here today to share with you some of our recent work on promoting human AI complementarity in decision making. So let's see. Okay, so we're going to talk about AI assisted decision-making scenario again. So in the past, given the decision-making task, it's usually a human who will process this task, deliberate about different decision outcome, and make a final decision. But today, AI models have been developed to uncover hidden insights from the big data. So now, given the same decision-making task, those AI models underlying the decision A's will analyze this decision-making task and provide some suggestions. And this suggestion may contain information like the recommended decision for humans to take, and it may also contain some assistive information, such as AI's confidence or explanation to its decision recommendation. Now, all this information will later be presented to the human decision maker, and it will be the human decision maker who makes the final decision. So essentially, this decision-making process has become a collaboration process between humans and AI. And of course, the promise here is that humans and AI each have their respective strengths and weaknesses, and through collaborating with each other, they can complement with each other and achieve a level of performance that outperform either human or AI alone. But in reality, what we find is that this kind of human-AI complementarity is very difficult to achieve. So very naturally, we wonder why this is the case. So over the past few years, my group has tried to conduct a number of empirical research to understand how exactly do human decision makers make use of AI models' decision recommendations in this collaboration process. And we actually find out a number of limitations of today's human-AI interactive dynamics. For example, in their collaboration with AI, human decision makers are often unclear about the decision-making competence of either the AI model or their own. And we also find that human decision makers may be struggling in making effective use of the assistive information provided by AI. For example, many researchers, including ourselves, have identified scenario where the presentation of AI models AI models explanation does not really help humans to calibrate their trust in AI and may even lead to some blind trust in AI. And finally, we also noticed that when humans determine whether they want to trust or rely on AI models' decision recommendation, a lot of times this decision is shaped by their cognitive biases. For example, if our human decision makers are not aware of the AI model's performance information, then they have this tendency to make use of the level of agreement between AI model and their own independent judgment on those cases that they feel confident about to gauge the trustworthiness of the AI model's decision recommendation, regardless of whether when they are confident about whether they are correct or not. So this kind of heuristic may be related to humans' confirmation bias. So with all these limitations that we have identified, naturally the next step is to think about how can we overcome these limitations and hopefully improve the human-AI collaboration in decision making. So one possible way is to actually design some interventions to change how humans behave. And this usually is a difficult approach, but I'm really glad to see that Hussein has already done some work along this direction. But we are also looking into an alternative approach, which is actually to change the design
designs of AI. So now, in order to better inform the designs of AI and AI-based decision aids, we think that maybe we should start from more computational understanding of the interaction between humans and AI by actually model these dynamics. For example, because we have already found out that humans are not really clear about the decision-making competence between, AI and themselves, maybe we should formally characterize or model the decision-making capabilities of both human and AI. And in addition, because we have this observation that humans are not really good at make effective use of AI's assisted information, then maybe we should look into how to model humans' reaction to different information so that we can present this information to people in a better way. And finally, we are also interested in modeling, humans' adoption of AI recommendations so that we can account for this kind of adopting behavior in the designs of AI. So now, if we have the models, if we have the computational models of humans on this aspect, in terms of changing the design of AI-based decision aids, there are many dimensions that we can play around with. For example, we can change how this interactive protocol between humans and AI is set by changing whether, when, and how to provide AI models decision recommendation to people. But we can also potentially change the AI models underlying the decision aids entirely so that we are effectively changing what kind of recommendations the AI model will provide to the decision maker. So in this talk, what I would like to do is to give you a couple of illustrating examples in terms of how we are able to model the human AI dynamics from all these aspects and later inform the redesign of the AI-based decision aids and ultimately making human AI complementarity possible. So let's start from this first project where we try to model human decision makers' decision-making capabilities and inform whether and when should we provide AI models decision recommendation to people. So as we said, ideally, what we really want in this AI-assisted decision-making process is that we want human decision makers to, cleverly combine their own independent judgment with AI models' decision recommendation by utilizing their strengths and avoid their weakness. But in reality, we see that this rarely happens. And of course, the key question now is how can we help humans utilize their strengths and avoid their weakness? And one very straightforward thought is that if we want to help humans utilize their strengths and avoid their weakness, we first need to let them know where their strengths and weaknesses are, especially in comparison to AI. So in this sense, it will be super great if on each of the decision-making tasks, we can estimate how likely human is going to be correct, as well as how likely AI is going to be correct on that task. Because if we are able to come up with this correctness likelihood estimation, then maybe we are able to guide our human decision makers to follow AI when AI is more likely to be correct and follow themselves when they themselves are more likely to be correct. But, this vision is really nice, but to realize this vision, we still need to address a couple of practical challenges. The first challenge is how can we actually estimate the correctness likelihood of human and AI? So AI side, maybe we can argue things are slightly easier because we could potentially just use the calibrated confidence score of AI as a correctness likelihood estimation. But what about humans, right? How can we model and estimate humans' correctness likelihood on different decision-making tasks in the real time? So that's our challenge number one. Now, challenge number two is even after we obtain this correctness likelihood comparison between human and AI, how are we going to nudge our human decision makers into more rational behavior, right? Either by following themselves or following AI. So that's our challenge number two. So now I'm going to go deeper into these two challenges and show you a little bit about how we managed to address these two challenges. Starting from the first one, modeling humans' correctness likelihood on a decision-making task for which we may not even know the ground truth answer. So this sounds pretty
difficult, right? If we don't really know the ground truth answer for the task, how can we really estimate how likely human is going to be correct on that task? So here we are making a very important assumption. So we are assuming that if a human decision maker's decision on the task that is similar to the current task is correct, this decision maker's decision on the current task is also going to be more likely to be correct. So this means that if we want to estimate this decision maker's correctness likelihood on the current task for which we may not know the ground truth, we can just look into how frequently this decision maker's decisions is correct on other tasks that are similar to the current task. And for those other tasks, we need to know the ground truth answer. For example, those other tasks may come from the AI model's training data set. So with this idea in mind, we came up with a 4-step workflow to estimate humans' correctness likelihood on different decision-making tasks. So we start by having this human decision maker complete a small set of decision-making tasks on their own. And using the data that we collect, we are able to learn a decision tree that essentially characterizes this decision maker's independent decision-making function. And then we extract the rules from this decision tree, present those rules to this decision maker. So if this decision maker sees some of the rules are not adequate to reflect their decision rationale, they can say, let me modify it. And eventually what we did is that using this user-modified set of decision rules, we predict what kind of decision this decision maker may make on each of the training task instance of the AI model's training data set and to whether those predicted decision is correct or not. So in the runtime, if we want to estimate decision maker's correctness likelihood on this new task instance, what we did essentially is we fetch a number of training task instances that are similar to this current new task instance. And so we estimate how frequently this decision maker is correct on those similar training task instance. So we use that frequency as our estimation of this decision maker's correctness likelihood on this current task. So that kind of helped us solve challenge number 1. But we still have the second challenge, right? How to communicate this estimation information back to the human decision makers. So perhaps one of the most intuitive thought is that we should just tell people directly. That's actually our first intervention here. So on the interface, we directly tell people, here is our estimation of how likely you're going to be correct on this task. Here is our estimation of how likely AI is going to be correct on this task. You can decide what you want to do. And so this serves as our first intervention direct display. But after we came up with this intervention, we thought maybe we should try other ways to communicate this information in a more subtle and indirect way. And we actually find this more subtle or indirect communication of correctness likelihood is possible. And important basis for this being possible is that some of the previous research have actually found out that certain interfaces, when they are used, they will decrease people's reliance on AI models' decision recommendation. But the drawback there is that they will decrease humans' reliance on AI, both when AI is correct and when AI is wrong. And that is not desirable, right? But now, because we could potentially estimate the relative performance comparison between human and AI on the task level, we thought that potentially we can communicate this information to people in a more indirect way using some adaptive interfaces. So this means that if we have some task instances that we actually estimate humans' correctness likelihood to be higher than AI's correctness likelihood, those are the moments we really want humans to rely on themselves rather than on AI. And those are the perfect timing for us to actually use those interfaces that will decrease people's reliance on AI. So with this idea in mind, we came up with 2 additional interventions. And the second intervention is adaptive workflow. And effectively what we did here is we adaptively change when we provide AI models decision recommendation to people. So in particular, if on the decision-making task, we find AI's correctness likelihood is higher than humans' correctness likelihood, we're going to show AI's decision recommendation upfront. Otherwise, we're going to have the human first to make a decision themselves,
and then show to the AI models decision recommendation. And this is precisely because some of the earlier research have found that after people have already registered their own independent judgment, showing to them the AI's decision recommendation, even after they see the AI model's decision recommendation, they're less likely to switch to AI's suggestion. Now, a third intervention that we came up with is adaptive recommendation, in which case we adaptively adjust whether to provide AI models decision recommendation or not. So if on the task AI is more likely to be correct, we provide both the AI's recommended decision and its explanation to people. But if on the task human is more likely to be correct, we only show to people AI's explanation without showing the precise recommended decision. Again, this is because previous research have suggested that when people only see the explanation, their final decision is less likely to be aligned with AI's recommended decision. Okay, so now we have 3 interventions, and we carried out a human subject experiment to see whether these 3 interventions can really help us improve humans' decision-making accuracy. And as you can see here on the screen, compared to this baseline condition, where we always show AI models this recommended decision as well as its confidence, in the other 3 treatments where the human decision makers are receiving our interventions, their final decision-making accuracy is marginally or significantly improved. If we dive deeper into the data, we'll see that this improve in the final decision-making accuracy is mostly caused by our human decision makers' decrease of over-reliance on AI when AI is making wrong decision recommendation. But when AI is making correct decision recommendation, the interventions do not affect people's reliance on AI too much. Okay, so that's the first piece that I want to show. Yes.
So what do you think from the 3 interventions would you recommend? So they seem to be equivalent, but which one do you think?
That's a very good question. We actually recently have some follow-up work on that. So my personal opinion is that probably these 3 interventions, their effectiveness will vary across context. And in the long run, whether they will be effective or not is also a question. So we actually have some recent work thinking of this as a multi-embedded problem. So, you have multiple different ways to present AI's decision recommendation to people. And over time, we're going to draw different arms and try to see whether it's effective or not. Yes.
How do you learn the topology of tasks? Like, how do you know which task is similar to which?
So we didn't learn on the task level. We only, for each of the decision-making tasks, we are estimating whether humans, like the chance for human to be making correct decision on that task, and AI's correctness likelihood is just a calibrated confidence.
Like the first part is about estimating humans' correctness likelihood, and for that, I think you rely on similar tasks.
Right. Okay. So that's a good point. So we are in this project, we are using some very simple Euclidean distance to determine the similarity of tasks. But I think a more sophisticated manner is actually to understand from the human's eye, right? Like what tasks are more similar, what tasks are more different from each other. Yes.
Can you incorporate into your modeling all risk of the decision? In other words, buying a pack of gum for $2 versus buying a car for $100,000, much higher risk. If that shifts the equations.
That's an interesting point. So in this particular project, we didn't really consider the decision stake. And we are only focusing on, the human's decision-making accuracy. You could argue potentially whether humans' decision-making accuracy is a function of the decision stake. That would be an interesting thing to look into. In some of the later projects that I will talk about, we do consider the decision stake, and the decision stake will at least affect how much humans are willing to incorporate AI's recommendation into their final decision. Yeah. Okay, so now let me quickly move on to a second project in which we try to model humans' reaction to information and determine, based on the insights, we want to determine how to present information to people in a better way. So in this project, let's consider this scenario that given a decision-making task, an AI model provides a decision recommendation, but we can further augment this decision recommendation by having a large language model analyze how each of the task feature might have contributed to the AI model's decision, final decision. Okay, so you will see that the language model will generate analysis like I'm showing to you on the screen. And in fact, if this large language model is the AI model that provides the decision recommendation, this large language model is essentially by giving out this analysis, you can think of it as its own explanation to its decision recommendation. So now the question is, we could have the language model analyze each of the task feature and generate many this kind of analysis. But how should we present this analysis to people in an effective manner? So we start with some really simple, naive approach to do it, right? So one possible way is that we just have language model in each time period, randomly pick a task feature, analyze how this feature may contribute to AI's final decision, show the analysis to people. People may interact by saying, I agree with this analysis, I don't agree with this analysis, and moving on, language model will pick another feature to analyze. So this is our first very basic naive approach. And our second very basic naive approach is just to have language model analyze everything and show all the analysis to people. So as you can imagine, when we ran the human subject experiment, we see that this two very naive approach of presenting language model-based analysis to people actually is not helpful in improving humans' decision-making accuracy at all, compared to a baseline condition where we just don't really show this analysis, right? So this really requires us to think harder about how to intelligently show additional information to people to hopefully improve their final decision-making accuracy. And to do that, what we started with is to model how human decision makers will react to this language model generated analysis. And we assume that our human decision makers, we assume that we can use a hidden state to capture the human decision makers' mindset or status as they consume all this analysis. And in particular, at the very beginning of this interaction, when the human does not really see any language model generated analysis, we assume that their initial state is only determined by the decision-making task and the AI model's decision recommendation. Now, as the human start to interact with the language model generated analysis, in each time step T, they're going to receive analysis RT from the language model on a particular task feature, and they will have some reaction to this RT by saying, I agree with the analysis or disagree with this analysis. And at the end of time T, they're going to update their hidden state, and this updated hidden state is jointly influenced by their hidden state in previous time step, as well as analysis that they see in the current time step, as well as their response to their current analysis. And finally, at the very end of this interaction, when the human decision makers need to make their final decision, we assume their decision is only influenced by their last hidden state in the last time step. So you can imagine that if we have a bunch of historical data about how humans will react to different language model analysis presented to them in different order and how eventually they make decisions, we can learn the parameters of this human behavior model. And that also means if we are encountering a new decision maker, we see their interaction history with the large language model, then we can actually estimate a distribution of this human decision maker's hidden state at the beginning of time T, right? We denote this as our state belief B of T. So now the question is, how can we, at time T, at this moment, our belief about this human decision maker's hidden state is B of T, and we have a couple of task features that the language model has not analyzed yet. Which feature we should have language model to analyze and presenting the resulting analysis to people, right? So in order to answer this question, we try to decompose it into a couple of steps. The first step we want to figure out is that we want to figure out what is our objective of presenting this analysis. Because we kind of know if we present different analysis to people, we may nudge humans into making different decisions. But now is effectively we're asking ourselves, ideally, what kind of decision we want the human decision to make? Well, what is the target decision we want to nudge human decision makers towards? Now, in the previous project, I've talked about one possibility of this nudging, determining this nudging direction is just to compare humans' capability and AI's capability, right? But now we are thinking about another potential way to determine this nudging direction, which is to come up with the theoretically optimal decision given AI's decision recommendation and humans' independent judgment or our prediction about humans' independent judgment. In fact, in the crowdsourcing literature, right, a lot of times we see this discussion about when we aggregate multiple crowd workers' judgments together, you get an aggregated judgment that is outperforming any of the individual crowd worker. So now, we are essentially asking ourselves, can we, use some analogy here to smartly aggregate humans' independent judgment and AI's decision recommendation together to form an aggregated decision. So we actually looked into a couple of label aggregation methods proposed in the crowdsourcing literature, like this David and Skin model, which tries to model each of the laborers or individuals' confusion matrix. We also looked into this GLAD model, which tries to model explicitly the task difficulty as well as the laborer's confusion matrix. And we also noticed a recent human AI combination method that explicitly tries to combine humans' categorical label with AI's probabilistic output. And they try to do so by model humans' confusion matrix and AI's calibration parameters. And we experimented with, this method on the real human decision data a bit. And we find that this last method, at least in our scenario, this last method, this human AI combination method, can actually produce aggregate decision that has the highest level of accuracy, robustly outperform human decision alone or AI decision. So we decide to use this human AI combination method to generate the target decision on each of the decision-making tasks that we want to nudge our humans into. So now we have the target direction in place. Then the next question is, given our target decision direction, and we still have a number of remaining features that we could pick to analyze, we should evaluate what's the utility or how much using each of the task feature can help us really nudging people into the direction of the target decision. So to do so, we quantify this by defining immediate expected utility given this analysis R and our current belief of humans' hidden state. And in this immediate expected utility, the expectation is taken over all the possible hidden states that humans may belong to at this moment. And inside the expectation term, the denominator is essentially saying, what is the probability for human to select the target decision at the end of time t-1? And the numerator is our expected utility or expected probability for human to select the target decision. If in time t, we present this analysis R to them, and we immediately ask them to make a decision by the end of time t. Okay, and you can see essentially for this immediate expected utility, if its value is positive, it means that we can actually increase the probability for the decision maker to select the target decision by presenting R to this person in time t. But a caveat here is that we don't necessarily need to have the decision maker make a decision by the end of time t. If we can actually show them more analysis and further improve their probability of selecting the target decision, we should do that, right? So then in this sense, instead of searching for analysis that will maximize this immediate expected utility, we really want to search for analysis that maximize the overall expected utility, which is composed of both this immediate expected utility representing, the probability increase in time step t, and the maximal expected future utility, which is the probability increase for the human decision maker to select the target decision, assuming that in all future time steps, we're going to use the optimal policy to select analysis. Okay, so this maximal expected utility, future utility term can also be computed in a recursive flow. So putting everything together, in order to answer, how exactly should we do in each of the time step t, essentially what we end up doing is that given the interaction history between the human decision maker and the language model, we first estimate what is our current state belief, what is the target decision we want to nudge humans into, and given our remaining set of task features that we haven't analyzed yet, we're going to compute the value of this maximal expected overall utility. And if this value of this maximal utility is a positive number, we're going to pick whichever task feature that makes that expected utility maximized, presenting it to people. Otherwise, we're going to not showing any analysis anymore, have the human decision maker make their final decision. Okay, and we again ran the human subject study on both the income prediction task and the recidivism prediction tasks. And what we see is that when the algorithm, when we use our algorithm to select what kind of language model generated analysis to be presented to people, we are able to improve human decision makers' final decision making accuracy, not only compared to the baseline condition where we never show the analysis, we show the analysis randomly, we show all the analysis simultaneously, but we also are able to outperform a heuristic baseline in which we show the large language model analysis based on a decreasing order of the task feature importance value. Okay, and when we look deeper, again, this suggests that our approach is mostly helping the decision makers to decrease their over-reliance on AI, but does not affect their under-reliance on AI too much. Okay, so in the previous two projects, we're pretty much thinking that, changing the interactive protocol between human and AI, but we are assuming this AI model is fixed. But in this last piece of the talk, I'm going to quickly show to you a scenario that we can actually model humans' adoption of AI recommendation, which will inform us to change or retrain the AI model underlying the decision aids. And using that, we can potentially improve the human-AI complementarity. So if we think about how AI models are trained today, right? So most of the time, the AI models are trained today to optimize their own independent performance. They are essentially ignoring the role that human decision makers are playing in this process, right? But this could potentially resulting in, not so great human-AI collaboration outcome, because it could be that the behavior oblivious AI model is super great on some cases, but humans will completely ignore AI suggestions in those cases. But in those regions that human really need AI's help, AI's performance may not be so good. Right, so now the question really is, how should we train AI to accommodate humans' needs and behavior? Our proposal, which accidentally coincides with Jen's proposal, is that we should really move away from training behavior oblivious AI and instead training behavior aware AI model. And this behavior aware AI model really need to account for humans' reaction to AI recommendation into AI's training objective so that we can directly optimize for the human-AI chain decision-making performance. And you can see that one important precondition for us to be able to do this optimization is that we really need to computationally model how humans will factor AI recommendation into their final decision. And we have made some exploration to this end. For example, we find that potentially we can model humans' willingness to adopt AI recommendation as the outcome of two steps, right? So first, given the AI model's decision recommendation and confidence, humans may be able to compute the utility for them to accept AI's decision recommendation or reject AI model's decision recommendation. And then they can map these utilities into some probability of either accepting AI or rejecting AI. But more interestingly, what we find is that in order for these two-step models to best fit the real-world human behavior data, we actually need to account for humans' own independent judgment as well as their own decision confidence in both the utility estimation and the action selection part. For example, if we are dealing with this decision maker, in this case, you see this decision maker actually disagree with AI's decision recommendation, and they're pretty confident about their own independent judgment. What we see is that this decision maker will significantly decrease the utility of accepting AI and significantly increase the utility of rejecting AI because the fact that their own very confident independent judgment disagree with AI's judgment makes them significantly lower their belief in how likely AI's decision recommendation is correct. But if we look at another decision maker, this decision maker also disagree with AI, but they are not so confident about their independent judgment. In this case, they will also try to adjust this utility, but the magnitude of this utility adjustment is going to be much smaller. Okay, and moving on, after this two decision maker compute their probability of accepting AI or rejecting AI based on their updated utility, they will actually further try to adjust those probabilities based on whether AI's decision recommendation agree with their own independent judgment. In our example, because both human decision makers are disagreeing with AI's decision recommendation, they're going to decrease the probability of accepting AI and increase the probability of accepting AI. But because this first decision maker is much more confident in their own independent judgment, this magnitude of adjustment is going to be much larger for the first decision maker and much smaller than for the second decision maker. So, yes.
Are the confidences and utilities computed by the humans before or after seeing the recommendation of the AI?
So in this case, we only show them the recommendation. We never actually ask them to make an independent judgment themselves. This independent judgment and independent confidence are our estimation or our prediction based on historical data. Okay. So if you look at this kind of example, effectively what we find is that our human decision makers are actually more receptive to AI recommendation when their own independent decision confidence is low. So in order to account for this kind of behavior in our AI training process, we came up with a simplified version of the human behavior model, which is this threshold model. Essentially, what it says is that when humans' own decision confidence is higher than the threshold tau, they're going to go with their own independent judgment. Otherwise, they're going to adopt AI model's decision recommendation. And it turns out under this particular human behavior model, the problem of optimizing the human AI team performance effectively becomes, we can transform it potentially into this problem of solving a weighted loss minimization problem. And the weight here, if we actually know what precisely this confidence threshold is, we are able to set this weight as essentially whether on each of the decision-making task instance, the human's own independent decision confidence is higher than the threshold or not. If their confidence is higher than the threshold, we set the weight associated with that training instance to be 0. Otherwise, we set that to be 1. But there are also the scenario that we don't really know the precise value of tau. We don't really know the precise value of the confidence threshold. In this case, if you assume this threshold is sampled from an underlying distribution, the optimal weight that we should assign to each of the training instance is actually 1 minus the CDF function value for humans' own decision confidence on the corresponding training instance. And if this, as a special case, if this distribution is actually a uniform distribution between 0 and 1, we can conclude that the optimal weight assigned to each of the training instance is 1 minus humans' own decision confidence on the training task instance. So to verify this, we again tried it out on the real-world image labeling task, and we carefully curated 10 classes from the ImageNet dataset. So you see that there are 5 classes that is relatively easily recognizable objects and 5 relatively challenging dog breeds classes. But not all the dog images are equally difficult, and not all the object images are equally easy. And we trained 2 models, one with this standard behavior oblivious AI model, and another is the behavior aware AI model, where we use this 1 minus human's own confidence on the training instance as our weighting function. And we are able to see that compared to the scenario that humans collaborate with the standard behavior oblivious AI model, when they are collaborating with behavior aware AI model, their accuracy is significantly higher. And when we dive deeper into the data, essentially what we see is that the behavior aware AI try to sacrifice their own performance on those object classes that human may not really need their help that much, but increased their performance on the dog breeds. This is particularly salient in the dingo and the gas pump classes. But if we look at humans' final accuracy, you see that in dingo classes, these dog classes, humans' final accuracy when collaborating with behavior aware AI is significantly increased. But when for this gas pump scenario, humans' final accuracy is not substantially decreased either, because humans may mostly rely on themselves for the judgments in those cases. Okay, so that's actually all I have, and thank you. And we'll see questions.
I have a question kind of broadly related to this agenda. So when you choose between different LLM designs, there is sometimes 2 ways how they can affect behavior. One is to use nudges, really use some behavioral patterns in human behavior. Another one is purely informational. That is, you choose different designs, maybe they will provide different information to humans. Maybe they will explain why they provide these recommendations or those recommendations more. Did you think about how to separate those 2? Because both of them could affect behavior.
Right. I think that's a very interesting question. And so far we are mostly thinking about changing the design of how or when the language model or AI's presentation is recommendation is presented to people. We're not really in the direction of changing the information or trying to release some of the, let's say, private information of AI to people. That's a very interesting future direction to explore, I think. And potentially, we could potentially come up with a general framework that model both types of ways as sort of one arm, let's say, one possible information exchange protocol between human and AI, and we can try out using this exploration and exploited method, try out which arm is most effective in which scenarios.
Yes, but even with your design, right? I understand if you display when the information is designed, I think it also affects what information is displayed just by design. Like it changes what the LLM produces. So I'm just worried that even that design contaminates these 2 things.
So you're saying that
or you control that it is exactly the same information is displayed.
Yeah, so in our scenario, it's the exact same
information. The text is just exactly the same.
Yeah.
I see. Okay. So that would attend that.
Other questions? This one.
Yeah, I also had a question about the algorithm for displaying the recommendations or the analysis and rationales. So your final algorithm, like, I think there might be like 2 benefits, right? It's like one, you omit the rationales that give negative utility. And then another bit is displaying the order to maximize utility first and then ordering by that. Like if you were to try to like qualitatively disentangle those, which do you think is more important? Or I guess like what is the kind of comparative contribution of both of those things in the final kind of big boost that you get in performance when using your algorithm?
Yeah, that's a very interesting question. You're essentially saying that the benefit of the algorithm is both coming from the selection of which analysis to show and also the ordering of the analysis, right? I don't have a good answer at the moment, but I think it's actually interesting question to look into. Like if we run the experiment with the precise set of analysis selected by the algorithm, but we flip the order of the analysis, we could potentially see the utility coming from the ordering part, right? Or we follow the same order, but maybe take out some analysis from the algorithm selected sets, then we may see the benefit from the selection of analysis. But it will be interesting to explore. Yeah. Yes.
Yeah, so the slide where you showed like the expected utility of the rejecting or accepting AI recommendations stratified by like the human confidence level. So is utility quantifying like the likelihood of the decision to accept or reject the AI recommendation leads to the like human AI combined target? Is that what the utility is quantifying?
Right. So at the very beginning, when we don't account for humans' independent judgment at all, we are assuming that humans are just treating AI's confidence as some probability of how AI is going to be correct. And behind the scene, we also have a decision stake saying that if their final decision is correct, what's the reward? If their final decision is wrong, there are some penalties. And they are just trying to compute, they can compute either expected utility or prospective, using some assumption of prospective theory to compute the utility. We actually try to work on that front.
Yeah, I just want to make sure I get the information here. So I saw like the difference in the expected utilities were different depending on the human's confidence level because
it depends on humans' belief of which option is correct. And this belief may be jointly influenced by AI's confidence, AI's recommendation, and later on, maybe if they incorporate their own independent judgment and their own confidence, they may adjust this belief as well.
Okay, thanks, Kate. Thank you. So our final speaker, well, let me let you get set up first.
I should join Zoom.
Yep. So we can give you.
Yeah.
You have it.
The speakers.
Oh yeah.
I'll get you.
Okay, so our next speaker is Keon Bapa. He's currently a postdoc at Harvard Data Science Institute. Before that, he got his PhD at Columbia, working with David Blay in CS. And his work is sort of broadly about interpretable machine learning, and in particular foundation models, often for social science applications. So he's done interesting work in things like generating rationales for generative model outputs, work on things like predicting job sequences, labor market or labor economics sort of information. He had a paper recently that you might have seen. It was very popular online about evaluating the world models that foundation models like LLMs can learn. So I think he had a nice image of, like in some cases, we might have some model predicting things like taxi routes, was it? Or in New York City. And so in that case, there's an easy way to sort of visualize what the model's learned. We can sort of show that, like it thinks that some streets are diagonal, et cetera. But what's nice that they provided is an evaluative framework in these many cases where we want to try to evaluate the implicit model of the world that some large language model or foundation model has learned, but there is no easy visual sort of analogy. And so that's a really cool piece of work he's done recently. Today, he's going to talk about sort of people's expectations about large language model behavior. So welcome, Hyun.
Great. Hey, everyone. First of all, thank you to Jessica and Jason for organizing this. This has been an awesome set of talks, and thank you all for sticking around. I know I'm what's separating you guys from lunch, so hopefully I won't need the full time, but we'll see. I'll just say. So this is work with Ashish Rambachan and Sundal Malayathan. So large language models. There are a lot of large language models out there. There are too many to count, but there's a conundrum, and this is a conundrum that I've been thinking about recently, and it's been sort of guiding some of the work that Jessica mentioned that I've been thinking about. And so let's start with the obvious. Large language models have done really amazingly on a large variety of evaluation metrics. They can pass AP exams, not just in English or history, but also in math. They can also help you code. And this is reflected in the evaluation metrics. And I think what is really impressive isn't just the level, but really the rate of acceleration. Like this chart shows how much these things have improved for the past couple of years. There's a very, very rapid rate of increase in these performance metrics. And
sorry to interrupt. You're not sharing the slides to Zoom.
Oh, okay. No.
People want to see them.
Good thing we know.
Go to the Zoom and share. And then, yeah, if you're not using presenter view, though. Sorry to interrupt.
No, that's important. Great. And is there any way to pull back? Click on the top. Click on what?
Oh, the X.
Okay. And so these metrics are capturing something real. They're not just, artificial metrics. And I think that everyone in this room has had an interaction where you use a large language models and see something truly, really impressive. Here, this is an example I like. This is from the Sparse of AGI paper. If you ask a large language model for a proof that there are infinitely many primes with every line that rhymes, it does a reasonable good job. This is it seems like a valid proof. It rhymes. It's pretty good. It's easy to be cynical about these, cherry-picked examples about LLMs, and maybe we ought to be cynical. That'll help us, improve them and drive research. But we really can't deny that they do some really, truly amazing things that we would have just thought impossible in 2017. But at the same time, they have a lot of goofy behavior too, that I'm sure you've all seen as well. So this is an example I like. If you give a large language model a set of possible itineraries, this is GPT-4, you're considering metro, train, and car, and you give the distance or the times and the travel durations and the costs, and you ask which mode of transportation should I take, GPT-4 starts by saying, okay, let's start by calculating the cost per minute of each mode of transportation. It does that for the train, car, and metro, and then says, great, the train costs the least per minute. So you should take the 395-minute train because you're getting the most bang for your buck as opposed to the 80 or 92-minute metro. And if the train was 500 minutes or 1,000 minutes, great, take that too. That's an even better deal. So this is the LLM conundrum, that how can we use these tools, these large language models, if they have this strange behavior? They have wow examples, truly amazing examples. They have goofy examples. And they have metrics that point to their capabilities. But given that we've seen the sort of wow and the goofiness as well, there's something that the metrics aren't capturing. So how can we even trust these metrics if they aren't telling something that's true to our experience of large language models? Well, so the good news is that we've seen this before. There have been moments where we've had astounding metrics and really impressive results. and also incredibly goofy behavior. And so to see that, I'm going to go back in time 10 years to the days of the good old days of supervised learning. Supervised learning had their set of metrics. Here's ImageNet, and we had, like LLMs, not only really impressive results, but really rapid improvement over a short period of time. We also had really impressive examples. This is an example I really like, that image classifiers can tell whether two pictures of pigs are the same pig or a different pig, and we can use that. And people have used that for improving farming and wildlife protection. But like LLMs, there are also these really goofy behavior that we've seen in these binary classifiers or supervised learning models, where the same kind of model that can tell you whether the two pigs are the same face, if you give it a pig, it'll tell you it's a pig. If you add a little bit of adversarial noise that to us makes the image look identical to the original one, it will say airliner. So this is one example of the goofy behavior of supervised learning models. These are adversarial examples. But so with both LLMs and supervised learning, we've had amazing metrics, really amazing examples, and some kind of head-scratching behavior that we don't really understand. Or at least we didn't understand, except we now do have a bit of a grasp on this for supervised learning. We've ironed out all these problems for supervised learning, so there's hope, right? That we can do the same thing for large language models. Well, let's go through and see how exactly we did get through this for supervised learning. So the key insight for evaluating supervised learning methods was this. If we think about a supervised learning method as a classifier F that goes from an input X to an output Y, the crucial question that is sort of underpins any sort of hopes to evaluate how these things will do when humans use them is, where will the classifier be used? And we had a solution for this in supervised learning that will use the classifier for some deployment distribution queue. And so if we evaluate instances that are similar or identical to this distribution queue, then theory will tell us that the behavior, barring distribution shifts, that the performance on P will match the performance on Q, or the performance on P will match the performance that we care about on Q. So for example, if you're the New York Times, you train a binary sentiment classifier on movie reviews for some reason, and you will only plan to use that binary sentiment classifier for other movie reviews that you hope will follow roughly the same distribution. And so you have some guarantees that if they follow the same distribution, that it'll perform well. So this deployment distribution is the sort of key that holds all of supervised learning evaluation together. For large language models, it may seem like we have the same setup. Again, we have a function that goes from X to Y. Here, X is the prompt. It's a question you may ask a large language model, and Y is its response. But the critical question here for evaluation is, where will a large language model be used? And it's not as obvious as in the sentiment analysis case for the New York Times I gave, because large language models aren't always just used for one thing, the thing they were trained for. Large language model, you can use the same large language model to write code in Java or Python. You can use that same model to perform clinical knowledge review. You can even use that same large language model to produce unicorns in TIGSI. So there's a whole diversity of use cases for large language models that far exceed those that they were trained to accomplish. And so there's a saying that I like, which is that this paper introduced this idea that GPTs are GPTs, general purpose technologies. You can use the same model for many things, and people have been using the same model for many things. So we can't just evaluate them on one thing that they were trained for, because they're general purpose. So this is the crucial question for evaluation of large language models. And it's something that I've been thinking about in sort of all different strands of my work, not just the one I'm going to talk to you about today. But in this talk, I'm going to focus on one example of where LLMs will be used. And the example will be the case where the deployment distribution isn't static. We don't have a sort of fixed data set like movie reviews from the New York Times. This deployment distribution is chosen by people. People choose where they're going to deploy a large language model, and so the reward they get depends on how they choose to deploy it. And so to evaluate how LLMs will perform in this setting, we can model how people how people or where people deploy LLMs. And I want to say this isn't just something that we can do, this is something we must do. To get to know how LLMs will perform in the wild when humans choose to use them, we need to understand how people are going to choose how to use them. And so that's what I'm going to be talking to you about today. It's sort of one example of how people can choose where they will and won't use large language models. And so how do we choose where to use large language models? Well, if you're like me, what you'll do is you'll spend a lot of time sitting down in front of your computer, ask GPT-4 questions, you'll try to break it, you'll see what it can do, you'll send some things to your friends, include some examples for talks later on, and then you'll form a mental model of what it's good at. You'll decide, okay, well, maybe this GPT-4 is good at sending emails, it's good at writing code. I'm not really going to trust it on doing fact checking for my history papers. And so I'll decide to deploy it for the tasks that I think it will perform well on after interacting with it. And so I just want to point out that this is different from supervised learning. And it's precisely because in supervised learning, we don't have a single general purpose technology. We have many different models that are trained for many different tasks. If you have a sentiment analysis classifier, you'll train one model on sentiment analysis classification. You'll have a benchmark for that. If it performs well, great, you'll deploy it. If not, maybe you won't. For machine translation, same story. You train a separate model. Maybe it does well, maybe it does poorly. With LLMs, because we have both a single model that can do many things and also many different tasks that aren't really well defined and don't have benchmarks. For example, we can't what benchmark would we even use to say which LLM is the best one at sending emails, or which LLM is the best one for helping me write related work sections for conference papers. So because we can't create a benchmark for every possible LLM task, we need to generalize what they're good at and what they're bad at after interacting with them. So the sort of thing I've been hinting at is that forming beliefs about LLM capabilities is itself an act of generalization. And this act of generalization isn't something unique to LLMs. We do this all the time with people. So if I talk to someone and I ask, maybe I ask Jessica, I ask her a question about quantum mechanics, and let's say Jessica answers correctly. Then I'll assume, great, Jessica is great at quantum mechanics. I'll go to Jessica for quantum mechanics questions. Is probably also very good at math and physics. I have no idea if Jessica can help me find a Chinese restaurant in New York City. So based on the interactions we have with people, we generalize the things that they're capable of, the things that they can help us with, and the things that they won't be able to help us with. We do the same thing with LLMs. We ask them questions, we interact with them, and we form generalizations. Oh, an LLM that answered this multivariable calculus question could help me answer a single variable calculus question. Or this LLM that wrote the proof about the infinitude of primes rhyming could also help me with a simple inequality. It can tell me if 9.8 is bigger than 9.9. And so these beliefs that we draw from interactions determine where people and for what tasks people will end up using LLMs for. So we formalize this idea with something that we call a human generalization function, which is a human's belief that after having seen an LLM answer one question, will answer another question correctly. So this is a belief. We can think of it as some sort of probability that people assign to an LLM answering a question correctly or incorrectly. So for now, just think of each X as each X is a question or a task, and it has either the LLM has either there's a correct answer or an incorrect answer. LLM either has a correct answer or it has an incorrect answer. So to give an example, X prime may be what is the quadratic formula? And so if we ask an LLM, what is the quadratic formula, and it answers correctly, which I'm using a check mark here instead of writing out the quadratic formula because I wasn't sure I could write that out 100% perfectly. So let's assume the LLM knows the quadratic formula. You then may form a belief about what's the probability that an LLM that knows the quadratic formula can tell me which number is larger, 9.11 or 9.9. And the reason I chose this example is because some of you may have seen this. This is like a famous example that GPT-4, at least throughout the summer, couldn't get right until some engineers at OpenAI decided, I have no idea what happened, but I imagine they sort of went through, jerry-rigged a few things and made sure that it started telling people that 9.9 was indeed bigger than 9.11. So we can imagine this sort of generalization function as existing over all pairs of possible questions. We can also generalize it. Here I'm just showing one question. We can also imagine it for a set of questions. Like after you've seen an LLM answer, 10 or 20 questions correctly or incorrectly, what are the beliefs that we have about how it'll perform on other sets of questions? And so where does the generalization function come in when we evaluate, and why does it matter? Well, so note that when we evaluate LLM performance, we're typically using a fixed deployment distribution. So this is the sort of setting of benchmarks or supervised learning. We have a loss L, we have a distribution P over instances we will evaluate on, and we have a performance. When we are evaluating models under human deployment, our loss or our reward doesn't depend on a fixed distribution over instances. It depends on this distribution about where I will deploy the LLM to, which we're calling H, the human distribution about where LLMs will be deployed. And so performance in the setting depends on a new kind of alignment, which is, can someone predict where an LLM will fail and succeed after interacting with it? So, put another way, if I, after interacting with an LLM, can figure out exactly the set of questions that it's good at and exactly the set of questions that it's bad at, then the second number will be large, because presumably I'll deploy this LLM to perform the questions that it's exactly capable of answering, and I won't do it otherwise. On the other hand, if I can't predict where an LLM will fail and succeed, our reward may be low, because we'll end up deploying it for tasks that it's incapable of, and we may hold it back from performing tasks that it is capable of. Yeah.
So here I think of X as being some kind of a problem space, and each X is like a problem that's given to the LLM, and you.
Exactly. Yeah. Yeah. You can think of X as a problem, or you could also generalize think of it as a task, like writing emails. This same thing.
So in some sense, I mean, I like this idea of. I'm wondering the representation. This X space really matters, right? Because you can think about a space where all the easy problems are nice, and and all the hard problems are here, and there's a linear classifier between them. Or if you choose a very different representation, it could look very complicated, and these could look very different depending on how you represent the problem.
Sorry, why do you say there's a linear classifier?
I'm just saying, depending on how you encode the problem space, like how you think about the problem space, because it's not clear how you're thinking about it, right? So, but depending on how you represent it or think about it, the picture could look very different about.
Yeah. So how is it being represented is by humans. It's like we maybe the simplest encode, like what we do in our experiments, is think about X as literally. Let's go back to the instance level. Think about X as a literal text of a question. And so you can encode that in your mind however you want, and you form a judgment about where it will perform well and where it will perform well. A point that maybe you're touching upon, which is obviously a very big glaring omission I have, is there's not one single human generalization function. We all generalize differently. So like the way that maybe you sort of encode questions differently than how I encode questions, leading to different functions. So of course that's going to differ between people. For now, or throughout this paper, we're just assuming that there's one fixed thing, or we're measuring this generalization function in the aggregate. We're averaging over people. Did I?
Yeah. If it takes too long, I think we could just.
Okay. I mean, while there's the Zoom, does anyone have any other questions? Yeah.
So one thing about your formulation is like usually if you like loss 0 is like perfect performance on that instance.
Yeah.
Something about this formulation says that like perfect performance and getting a human not to use it on that task are somehow equally good.
Yeah. So this is very general, and there are cases where that will be the case. You can also maybe think about L as a reward instead. So there's going to be positive or negative, and maybe you're not averaging, maybe you're taking this off. So these are different possible instantiations. Yeah.
In a certain sense, this is kind of hinting at the idea of factual knowledge versus procedural knowledge inherent within the human generalization function, because using the example that you just gave, a quadratic function, you can simply search it up. It's a fact that exists in the wild. While the knowledge of figuring out how to read fractions is not necessarily encoded.
So I guess what's the difference between, I didn't catch the difference between the fraction and the quadratic formula?
Right, I guess I was thinking, like, the quadratic formula is something that's more factual, that you can just look it up.
Yeah.
While, the other one, it's not necessarily something that you can directly look it up per se,
Well, which one?
the 9.11 versus 9.9.
And so you're saying that like there's probably somewhere, you know, however it's trained online, like there's probably a place where it's come across that says like, this is a quadratic formula, but it maybe hasn't seen anything that is like, you know, is 9.19 bigger than 9.11. Yeah, so that of course that's true. And so this is sort of you know, either of those cases can fit in here. I guess there's a larger question, which is that we're sort of assuming that things are either true or like things are either correct or incorrect. And so you'll need to have that assumption to make sense of this for any of the examples. Sorry, let me just figure out, I don't know why I got
think you just got kicked off. What network are you on?
I am on EduRoam.
Yeah, that should usually be reliable. Yeah, I guess try one more time, and if it continues to give trouble, just make sure your audio is muted. Sorry about that.
No. Okay, does this work? Or have I shared my screen? Oh, I have.
You're good.
Okay, great. Okay, fantastic. And so you sort of what I was hinting at before is why this notion of alignment is important. You know, there's a general theoretical result, which is actually, you know, quite a simple example. We can, if you define dominance as, you can define dominance relationships as occurring, you could say LLM1 dominates another LLM2 if every question that 2 answers correctly is also answered correctly by LLM1. So let's call this a dominance relationship. Notice that dominance relationships are preserved when we are performing, you know, standard evaluation against the fixed deployment distribution. So if you have a sentiment analysis classifier that's better than another one, and you're evaluating over the same static set of points, the one that dominates will always be better. But with LLMs, with LLMs under human deployment, that may not be the case. And this is because with LLMs, recall, people are choosing where, in this framework, people are choosing where to deploy them. This function H depends on F. So here you can have the LLMs where one is better than the other one at every single question it answers correctly. This one also answers correctly, and have the other one perform worse when it's being deployed in the wild. And the reason for this is exactly due to misalignment. Because people's reward depends exactly on what questions the LLM is being asked and what it's being deployed to, one that you can figure out what it's good at and bad at may be better off than one that is maybe better on benchmarks and better at each individual thing, but you can't figure out what it's bad at and what it's bad at, what it's good at and what it's bad at. So this is sort of the slightly more formal point of the one that of why alignment is important. So hopefully, these sort of this framework has made the case for why it's important to think about human generalizations when we're evaluating LLMs to understand where they'll go, how they'll be used. The challenge was there isn't really good data about what generalizations humans make. I mean, we each have our sort of own function. It's sort of hard. I can't like enumerate my own function. I can't, to the question earlier, like I can't differentiate through my own human generalization function. It's somewhere latent inside of me. But so we collect a large data set about how people form these generalizations. And so we ran a survey on Prolific where we took questions from about 80 different LLM benchmarks, and we showed each respondent 2 random questions from the benchmark. We first showed them a question and we said, assume an LLM saw this question and it either answered correctly or incorrectly. How do you think it will, what do you think is the probability that it will respond correctly to this other question? So based on this, we can sort of draw pairs, we can get pairs about how people generalize. And so to give you a few examples, so these are examples of things that of data points that we collected in the survey. So people are seeing the question on the left, they're being told that an LLM answered the question on the left correctly, and they're being asked, how do you think that same LLM will answer the question on the right? And so there's a saying that after people see that the first one is answered incorrectly, people will have a downward change in belief that the second one will also be answered, or that will be answered correctly. And so this makes sense. We think that an LLM that answers a chemistry or biology question incorrectly is probably going to perform is probably going to answer incorrectly to another chemistry or biology question. But of course, not every problem has to be related. Many, in fact, most of the pairs of questions were completely unrelated. So this is after people see a question about a TV sitcom or show, I don't know what My Three Sons is, they see it answered correctly, they don't have any change in belief about whether that same LLM can perform arithmetic. So we have unrelated problems, and we also have asymmetric problems. So for this question, we have sort of a problem that I personally would think of as easy, which is just counting how many objects there are on a nightstand. And on the right, we have a question about vitamins and coenzymes. And so when the first question is answered correctly, people don't really update their beliefs that it answers the second question correctly. I think you could justify this as saying, oh, like this is such an easy question that it doesn't really tell me if a human answered the question on the left correctly, I wouldn't really assume anything about their vitamin capabilities. But if it answers it incorrectly, they'll say, wow, this LLM can't even count. There's no way that it's going to know what a coenzyme is. So with these examples, we can ask, how do we actually generalize? And so here I'm plotting humans form confidences about the probability that each answer will be correct or incorrect after seeing how an LLM responded to another question. And I'm plotting the actual correctness of that question. So this is sort of like a human's posterior belief matched against the true probability that it's correct. And so to give a sense of to give a baseline, I'm also including the blue line here is how a human would respond. Is humans generalizing humans? So we also survey humans. We ask them the same questions that we ask LLMs, and we say, do humans who get this question right also get this question right, and vice versa? And so this is for a subset of the data. And the first thing to note is that our confidence tracks pretty well with people. As we're more confident that a person's answer will be correct, that person's answer actually is more correct on average. But we don't have that same sort of nice relationship between for LLMs. Our confidence is much less correlated with the probability that an LLM will answer a question correctly than it is for people. And scale alone doesn't fix the problem. So here I'm plotting 3 different large language models. There's a Llama 2 model from Meta, and each one is a different size. So as we go from 7 to 13 to 70, you're getting larger and you're getting more capable, at least in terms of the metrics. But we're not seeing that much change, if any, on our sort of alignment with how well with how well humans generalize the answers to these models. So we can also look for examples of
what were the columns in that picture?
So there's 3 columns. This is just grouping posterior beliefs into 3 categories. On the left is humans are confident that the answer will be incorrect. On the right, it's confident the answer will be correct. And then in the middle, it's sort of roughly 50-50.
And we're measuring the accuracy that belief is correct, or what's the bias?
So it's like of the things that humans, so like let's say this middle column is 50%. This saying of the questions that humans believe that an LLM had 50% accuracy of answering after having seen the first question, what percent are those correct? So it's sort of a calibration. It's a posterior calibration. And so we can actually look at examples about what are examples of generalizations that people are or misgeneralizations that people are performing. And so all of these sort of have structure that intuitively makes sense to me. And I want to stress that these are examples that make sense. These are there are also examples like this that just totally do not make sense, that are sort of hard to interpret, hard to parse.
So just because I may have missed that. So when you have the human thing, is it the human does badly on things where the human thinks that the human is wrong? Or the human does badly on cases where it thinks the LLM to be wrong? So are humans really imposing beliefs about their own ability when they evaluate an LLM?
Yeah, so the blue is humans evaluating humans. So you're always evaluating the same thing. Blue is we're measuring the same generalization function.
So I think I understand what I wonder what the categories are for the columns. So confident answer will be inaccurate is the human thinking that the human is okay.
Yeah. Or LLM. It's sort of, do you think that we ask, do you think an entity that answers this question will answer it correctly? But yeah, it's the human's posterior belief.
Okay, just to make sure. So when the column that says confident answer will be inaccurate, just looking at the blue one, this is a human who has stated that the human thinks the LLM will do it fully, or the human stated that the human will do it?
It's measuring the human to human, but we pose the same question to human and LLM. So we're measuring the same function for a human and an LLM. We're saying, do you think someone, either a human or an LLM, that answers this question correctly, will also answer this question correctly? I see. But you could also, do obviously these functions might be different, so you should do that. You can do that too. Yeah.
Here, so you did have these tasks that seemed incomparable, but there's a human belief that one is easier than the other. Does this experiment make sense when you only look at tasks that are somehow comparable, like subtasks of each other?
Yeah. You're saying that for most pairs of tasks, there isn't change of beliefs. Is this what you're saying?
I mean, for human beings, maybe there's a change of beliefs, but they may not actually be comparable, right?
Yeah. So this figure is just subset. This is a subset of the examples where there are changes, or this kinds of tasks where there are changes. And so if we look at what misalignment might look like, we see, these are we see examples where we would think that humans who get one right would get the other one right, and they don't. So like the middle one, for example, is we have a logic puzzle about people on a football team playing different positions, and Llama, a large language model, answers that right. When we slightly change the details, slightly change what positions people are playing, but keep everything else the same, the model gets it incorrect. And so I want to stress that none of this is anything new. This is this is just giving us a framework for thinking about goofy LLM behavior that we've all seen before. So one example of this that I like is the reversal curse, where if you ask an LLM who is Tom Cruise's mother, it will respond correctly that Tom Cruise's mother is Mary Lee Pfeiffer. But when you ask who is Mary Lee Pfeiffer's son, that same LLM will respond, I don't know who, I have no idea who Mary Lee Pfeiffer is. And so we can think of why we find this result so goofy as being due to the fact that, we have this generalization function where we think that, some entity that knows who Tom Cruise's mother is should also know that Tom Cruise is is his mother's son. And so these sort of false generalizations, why they might be, why we may want to avoid them, is because these beliefs guide how LLMs are used. So if we're drawing false generalizations about how LLMs are about what LLMs are good at and bad at, based on misalignment, as we saw before, we could see worse performance. And so I'm going to describe one exercise where we simulate what that performance would look like in one setting. But for that exercise, I want to talk about predictability, which is we have this function B. We have examples from this function B that take as input a question or a pair of questions, and the output is a belief. So one question you may ask is, how predictable is that function? We could treat this as an NLP problem where we're trying to predict some output, like whether someone changes their belief based on the text of a question. And so we find that this function actually is quite predictable. Not perfectly predictable, and as we get to larger and larger models, models actually do worse, but we can somewhat reasonably guess what are the pairs of questions that humans will update their beliefs on, and what are the pairs of questions that humans won't update their beliefs on. And so given this model, we perform an exercise where people first see how an LLM responded to one question. So maybe we ask a question, what's sin x squared, cosine x squared, LLM answers it correctly. And we then use this model of human generalization to form confidences that that same LLM will be accurate on all other questions. So for every new question, we have a prediction of what belief do humans assign an LLM of being correct, that same LLM of being correct on this new question. And then so to see how to simulate deployment settings, we can ask, if humans deploy LLMs to questions where their beliefs are above some deployment threshold, how well does the LLM do in those settings? And
yeah, I think it's related to this, but it's so you have this generalization function that has two questions as an input.
Yeah.
Like in reality, as you mentioned, people play a lot with this model. They have a lot of questions. So how do you generalize your generalization function?
Yeah, so that's a good question. So all these experiments are just for single pairs of questions. You could under Bayesian models of updating, you could just sort of chain the x's and x primes. You could sort of say that I have a level that gets updated every time.
Then you must know correlation structure, which you do not.
Yeah, I'm saying this is under an assumption of Bayesian updating.
range of data can be used.
Sure, yeah. In practice, you can also fit a model for multiple, you can think of all these same ideas work for multiple questions. You just have to fit a model that predict from multiple questions how do people believe something will be correct or incorrect.
Yeah, but then if you're infinite space, you cannot estimate it.
I mean, this is the magic of large language models and machine learning. Predicting functions of text should be in a possible space. Even this X and X prime space should be impossible. But the fact that we can do well on it sort of shows that there is some latent structure that these things are capturing. So we run this exercise, and so here we show at different deployment thresholds how accurate are different LLMs. And so on the left-hand column, this is just saying that human accuracy at predicting so the way to think about this table is this is the accuracy of the questions that people deploy LLMs to based on our model of the generalization function. And so on the left-hand side, we say that we find that when we deploy to questions where the implied deployment, where the threshold is about 50%, first of all, no one model performs very well. We get about 57% for the best model. As we go further to the right, we can think about this as increasing the cost of false positives. This is increasing the implied deployment threshold for deploying LLMs. And so when we find that as we make the implied deployment threshold higher and higher, statistically better LLMs perform, such as GPT-4 and 3.5, will perform worse when deployed by humans. And so this is saying that when people are forming confidences about what LLMs are good at and what they're bad at, if we're only saying I can only deploy LLMs to things that I'm nearly certain they're going to be good at, we get better performance with the smaller, less capable LLMs. And so the reason for this is that if you look at this exercise where we're giving people a question first and using that to decide what to deploy to, the larger LLMs get that question right more of the time. So it leads to false confidence more often precisely because they answer that first question more correctly than the smaller models. And so because of that, as the cost of false positives increase, we sort of see this behavior where smaller models get deployed for only the ones that they will actually get right based on what they got right for the first question. And so the performance on average is better when deployed by humans. Yeah.
But again, this claim is heavily driven by the assumption.
Yeah, this is the average point.
That like not predicting and being right are equally good.
Yeah, exactly. So you can play with different loss functions, and it's not clear to me that you wouldn't find this behavior when you have those different sets of loss functions as well. Yeah.
Why should we expect human beings to know whether an LLM will answer it right or not based on another question? Because we don't understand why they work, right?
Yeah, no, that's exactly the point. But we do this. Like if you go to, like consulting firms like, I don't know, like BCG or McKinsey, they're deciding like, this LLM, when I play with it, it looks good. It's good at answering math questions. So I'm going to deploy it on new consulting cases because I think it's capable of doing this. Like, even though we don't do it in sort of this like granular setting on the question by question level, I mean, or we do, maybe we do already. Like we're already doing this. We're forming mental models of what they're good at and what they're bad at and deploying based on that.
No, and also, I mean, it's also a question of who you've asked, and it also depends on whether the human was trying to judge whether an LLM will predict it right or a human being predicts it right. Because, if it's someone who knows machine learning, they would say, well, it depends on whether these kind of things are well represented in the data set.
Yeah.
If there's a lot of training data on these kind of topics, then maybe an LLM will do well, but, maybe it's not going to get it right on a very simple task, which is very, very rare in the data set.
I mean, another point that you're sort of alluding to, which is important, which is that, if we're thinking about sort of delegation, like we want to do some things with LLM, some things with human, what matters is not the accuracy of the LLM, it's sort of how much better are we at generalizing humans versus LLMs, and how does that match with the performance? So that's another good question. Okay, so I want to wrap up. This paper was, the conundrum that I pointed out in the beginning was about evaluating LLMs requires modeling where and what kinds of questions they'll be used. And we sort of saw that for supervised learning, this was a big, innovation and helped us think about the kind of goofy behavior. So we considered a setting where LLMs are deployed by people, and these deployment decisions were driven by this object, this human generalization function, which depended on one kind of alignment, which is how well can humans predict where an LLM will succeed after interacting with it. And so we saw empirically and theoretically that more capable models perform worse in practice precisely because of misalignment. And I want to point out that this idea of the human generalization function isn't only applicable to research, it's also applicable to daily life. So when this happened to me a couple of weeks ago, I saw that OpenAI released this new model O1, which was very capable of performing reasoning tasks. And the metrics that it performed were quite good. It did really well on AME competitions, on PhD level science questions. But the same model that can get an 80% accuracy, 83% accuracy on the AME, it also, this is from a post from Yunqin Deng, it also struggles at doing multiplication after you went beyond 5 or 6 digit multiplication. And so this is exactly an example of human generalization failure that I had when I saw this, which is thinking that, oh, of course something that can do well in the AME can do well on multiplication, and that's not the case. So, with that, thank you, and our data set is available online.
So it seems to me one motivation for this work is we want to design a metric that characterizes LLM performance and obeys this dominance relation. In practice, evaluation is sometimes done by just asking people to compare a pair of LLMs and ask identical questions to them. Like, could you elaborate on what's the implication from the?
Yeah, so I would say if you're always asking LLMs the same set of questions, that's an example of a static deployment distribution. And so this doesn't apply. This is sort of saying that where you apply the LLM, where you deploy the LLM to depends on how it does on other things. Is LLM specific. So I would say when you're asking the same sets of questions to each LLM, you're sort of back into the supervised learning evaluation framework, which is exactly sort of what the traditional metrics we have right now are, with the first slide dimension.
Can I ask a question from Zoom?
Okay.
Thank you,
guys.
Thank you.
Just two final announcements. So Mira has parking passes. If anyone parked in the garage and wants to not pay for it, we have parking passes. And the second announcement is for students who'd like to meet with the speakers. There are student meeting with the speakers from 2 o'clock to 4 o'clock in the order they presented in for half an hour each. In a meeting room that's at the far end of the building. Find a local student here. If you local students, put your hands up. You can follow one of them to where the space is.
Certain number?
It was 3014. Cool. Thanks everybody for coming. And lunch is outside.
Thanks to the organizers, Jason and Jessica, for organizing this workshop.
We've got great speakers, so. I love how you wrote it on your website and you still have a version of it. You're really good when you write.
I thought like you're not saying that it's gonna worse. I admit so you're saying that
I do that, but
I
I
thought
like doing that.
because I mean there's also statement that I thought
I got excited.
Yeah,
I was.
It doesn't mean that.
Oh, I see.
So to me that you allow the.
Everyone has to. Okay, cool. I'll see you at lunch.
That you don't have much time on the workshop, but, that's totally.
Oh, yeah.
It's like.
So, first of all, there are so many ways. I think the safest thing to do is to go back to the supervised learning framework where, well, this is very limiting, but it's safe. It's saying I only care about a certain set of things. But I only care about using an LLM for classifying which is spam or something.